Hello. Sir,
Yes,
you're
traffic.
mute, sir.
Yeah, am I audible now?
Yes,
Yes,
sir.
yes.
Okay, okay. So very good afternoon one and all. I myself, Dr. Manoj Sahani, welcome you all to this final day of the Faculty Development Program on Smart Manufacturing and Digital Transformation in Industry 4.0. I hope the past sessions have been insightful and have enriched your knowledge. So as we move through today's schedule, I would like to share some important information to all the delegates. So after finishing off all the sessions at 6:30, it is requested to all the delegates to fill out the feedback form, both which is shared by us in the chat as well as in the WhatsApp group. We'll be sharing this feedback form. Okay. As well as you need to fill up the feedback form in the AICT ATAL portal also. So there will be two feedback, one which will be shared by us and the other you need to fill it in the AICT portal. Now this is very crucial for generating the certificate. So following that, you will be having a half an hour examination based on the sessions that is being conducted from day 1 to day 6. And that examination link will be shared to you all in the Google form, which again will going to update in at 6:30 or 6:30 p.m. It will be around 6:45 because 15 minutes will be giving it to you for filling out the feedback, and the second at 6:45 will be sharing you the examination link when you will be filling that feedback form after completion of that feedback form. So you will be giving we will be giving you half an hour for the examination, and that will be from 6:45 to 7:15. And again, we'll be sharing that in the chat as well as in the WhatsApp group. So I request you all the delegates to please take note of all those things. Okay. As we have already shared to you all, for the generation of the certificates, three things are to be taken care of. First, the attendance should be 80%, and we'll be updating that attendance by today evening. Second is the feedback form, which is to be submitted. And the third important thing is that the score should be above 70% in the final examination that will be conducted today. So I think that will be clear to you all. We have already updated it in the WhatsApp group. So with that, we will begin this final day with enthusiasm and make the most of the remaining sessions. So thank you and have a great day ahead. So do begin this final day of our faculty development program on smart manufacturing and digital transformation in Industry 4.0. I would like to invite Dr. Krunal Mehta sir from PDEU Gandhinagar to introduce our first esteemed speaker of this final day and also one of the conveners of this faculty development program, Professor Vishwesh Badekar sir. So over to you, Krunal sir.
Thank you, sir. Warm greetings to one and all present for the session. It's my privilege to introduce Professor Vishwesh Badeka. Sir is currently the professor at the Department of Mechanical Engineering, School of Technology, Pandit Deen Dayal Energy University. He also holds the position of Dean Academic Affairs at PDEU. With an extensive academic background, he holds a BE, ME, and PhD in Metallurgical Engineering from the MS University, Baroda, and a diploma in International Welding Engineering awarded by International Institute of Welding. His research areas are vast and impactful, focusing on additive manufacturing using welding, friction stir welding, hybrid welding, ultrasonic welding, and welding of hybrid joints that includes metals and plastics, among various others advanced welding techniques. Over the years, Professor Badeka has received research funding from esteemed agencies like ISRO, DRDO, DAE, BRFST, BRNS, and DST, amounting to approximately 1.5 crore Indian rupees. He has successfully completed 5 sponsored R&D projects and is currently working on 4 ongoing projects. His contributions to academia are equally commendable, having guided 40 MTech and 10 PhD scholars, me being one of them, and with 4 more PhD students currently under his supervision. He has published over 100 international journal papers and book chapters, presented at 65 international and national conferences, and co edited the book titled Advances in Welding Technologies for Process Development, published by CRC Press, Taylor and Francis Group. Beyond academia, Professor Badeka has delivered 100 invited talks, conducted 12 workshops, and is an active member of several prestigious professional bodies like IIW, ISNT, ISTE, IIM, IIF, MRSI, and AWS. His exceptional contributions have earned him numerous accolades, including Dr. Vikram Sarabhai Award 2009-10, Panthaki Memorial Award 2010 and 2012, and several Best Research Paper awards. He also holds 2 patents in advanced welding technologies. Today, he will be sharing his expertise on the topic of advanced welding technology. So, please join me in welcoming Professor Badeka on the virtual stage. Over to you, sir.
Yeah, thank you. Thank you, Dr. Mehta, Dr. Sahani, for this wonderful introduction. And so I'll begin with the talk. So kindly please confirm whether my voice is audible and whether the slide is visible or not.
Yes, sir.
Yes, sir. Is it visual?
Fine, fine. So good afternoon, everyone, and thank you very much for this wonderful uh, uh, workshop, wherein I am also there as one of the speaker. So today we have two different sessions. One is on Advanced Welding Technology 1, and another one is Advanced Welding Technology 2. So without taking much of your time, I would like to begin the session. So my two talks are distributed in two different parts. I'm friction-based welding and friction-based processing. So moving further, this is the top, which is, I mean, yeah. So as you know, we have on the first day of our program, I made a short presentation about the IIW-PDU collaboration that we have. So under this collaborative efforts, we are working in a different areas of advanced welding technology, beginning from advances in fusion welding processes, I mean, activated flux stick welding, metal cold arc welding, flux cold arc welding, application of this code wire in narrow groove conditions. In addition to that, the solid state welding processes like friction welding, friction stir welding, friction surfacing, and use of welding processes for additive manufacturing. So this is general slide which talks about some of the key research activities, ongoing key research activities of the our group. So as far as today's presentation is concerned, I would be discussing, this is a content which has been planned for 1 hour, I mean, planned for this session 1. And there are some other content which has been planned for another session. So the classification of the welding processes, then challenges of dissimilar metal joining and friction welding, friction stir welding technology, wherein you can have a two different part, welding and processing. Our today's focus is in welding. I mean, the first session is focusing on welding part, and the second session is focusing on processing part. So moving further, I will be talking about mainly on friction stir welding for dissimilar metals and materials, friction stir welding variants. Under the variants, I mean, assisted FSW, twin stir FSW, bobbin tool FSW, dual rotation technique. Then another important process in friction stir welding called friction stir spot welding, refill FS friction stir spot welding, pinless, double-sided, and finally the friction stir scribe welding and stationary shoulder FSW. So the whole focus in this first module is on a welding side. So so to begin with, I would like to start with the classification of the welding processes. As you see, the classification includes solid state welding processes and fusion welding processes. And when you say fusion welding process, which includes like there is a typical metallurgical phenomena which happens and which is similar to the casting operation, melting and solidification. Since this melting and solidification happens in a very localized area in fusion welding, it is sometimes also termed as localized, I mean, fusion welding is a localized casting also. So melting and solidification phenomena happens in the fusion welding, while those phenomena remain absent in solid state welding processes. So since the melting and solidification phenomena is part of the inherent part of the fusion welding processes, you may tend to get the porosities, oxidations, micro segregations, hot cracking. These are the problems you may get depending on the metallurgy of the metals and the kind of the shielding environment which has been given to during the process. These problems are not there in solid state welding processes. You don't have a porosity there. You don't have, I mean, the hot cracking problem. That's how solid state welding's been preferred over fusion welding process. And the last and the most important benefit of solid state welding is it is suitable for dissimilar metal joining. I mean, now currently industries are looking for dissimilar metal joints, say aluminum to steel, copper to stainless steel, aluminum to magnesium, copper to magnesium. So there are many dissimilar combinations are required for various engineering applications. So these dissimilar combinations are difficult to join with the help of fusion welding processes, and but it's easy from a perspective of solid state welding processes. So this is what the fundamental difference between the fusion and solid state welding process. So one has to understand the fusion means there is a melting and solidification, and which is not there in the solid state welding process. And since the melting and solidification is there, the chances of having a porosity, oxidation, segregations, hot cracking. So those problems you don't have in the solid state welding process. And the most advantageous of solid state is the joining of dissimilar metal combinations. Moving further, our today's focus, I mean, we would be talking more about a solid state welding processes and specifically on a friction based processes. Now, if you see in this slide, I have mentioned that this solid state welding processes are suitable for dissimilar metal joints. But I mean, why it is, I mean, fusion welding processes are not suitable for dissimilar metal joining. Can you mix oil and water? It is not possible. So if you take a two different metals and they are not mixing in each other properly, right? So it's very difficult to join them. So there are certain challenges. Now, these are the challenges, if you see, these are the challenges which will be posed when you go for a dissimilar metal joining through the fusion welding route, right? So before you take two different metals, you need to see that whether these two elements are soluble in each other or not. So you need to refer the phase diagram, and through the phase diagram, you will come to know that whether these elements are soluble in each other or not. So if they are not soluble, right, or if they have a limited solubility, you may get a problem of segregation. Segregations may also lead to a problem of heterogeneity, right? So this is the problem which happens because of the improper solubility or limited solubility. Now, this limited solubility may lead to a formation of intermetallic compounds also. Now, these intermetallic compounds may to a certain extent, sometimes they are brittle in nature. And these brittle natures will reduce the impact property of the joints. Third, and the most important, is the corrosion. I mean, when you take two different metals, if they are very far in the EMF series, they may tend to give you corrosion related problems also. And the fourth one is if there is a mismatch in the mechanical property, if there is a mismatch in the thermal property, then you may also tend to get the distortion, warpage, residual stresses, and the thermal shock and the quenching cracking. Now, these are the problems which I have highlighted in the form of table to, to give you a perspective that dissimilar metal joining through a fusion welding processes is always a challenge. I'm sure you all know what are the fusion welding processes. Fusion includes your all arc welding processes. In arc welding, you have a MIG welding, TIG welding, submerged arc welding, plasma arc welding, right? All those arc welding processes you have, they are all fusion welding. Fusion means there is a melting of the filler metal, there is a melting of the base metal. So fusion welding, if you go for a dissimilar metal joining, and if these conditions are not satisfied, right, then there is a challenge in joining the dissimilar metal. But still, if you want to join, even after having these challenges, then you need to go with the solid state welding processes. So this is a background which has been from a metallurgical perspective, you can say, or from a mechanical perspective, you can say. These are the two background slides probably may help you to understand the subsequent part of the presentation. Now, the mother process. Now, in friction, I mean, in solid state welding process, the mother process is the friction welding. through the friction welding, many other processes have been invented, right? So if you see here, there is a, you can see there is a chuck and there is a dead end, and you can bring two surfaces in contact with each other, right? You try to visualize a lathe machine. You have a rotating chuck, you have a dead end. You bring two components, right, in contact with each other. Once you bring them in contact, because of the contact, there is a friction. And because of the friction, you can see that the interface become red hot, right? And then when you hold at that particular situation for a certain period of time, right, you can see that the temperature builds up. And then you apply some more force, which is F2. You can see there is a ring formation or an upset which forms at the interface. So the actual component you can see here, right? This is the actual friction welded joint of carbon steel, which has been welded on a lathe machine. So on a lathe machine, you can demonstrate friction welding, but commercial friction welding machine has many control. In lathe machine, you can have only control in terms of the RPM, while the force you cannot control. This is all you need to go for a trial and error basis. You can control only the RPM and the time of friction, while the rest all you need to do trial and error. Now, moving further into the friction welding part, because why I'm explaining you this process, because this is the mother process. From this process, the other processes were invented. So this is friction welding. Again, in friction welding, there are two types you have. One, which is being displayed in this slide, which is called rotary friction welding. You rotate and you join them. I mean, components, they are with the circular geometry. One of the components should be circular geometry. You can go for even linear friction welding also. I mean, the linear motion also helps you to join the interfaces. So I have a small video clip here, which probably may help you to understand. Now you see, this is the process. Can you please confirm whether the video is running properly?
Yes, sir.
Yes, sir. Yes, sir.
Okay, fine. Now you see, there is a video of friction welding, rotary friction welding, which is going on here. And this is what is a friction welding process. You can see the ring formation, and there are many combinations. As I mentioned, one component has to be rotating and circular. You can see you can go for a dissimilar geometry also. You see the material is same, but geometries are different. The conventional one, what you are observing with the circular geometry, which you can do easily on a lathe machine. This is a friction welding that. So now here also, there is another possibility that you have. You see that there is a linear motion. Now you see here, there is a linear motion which is going on between the two interfaces. And these linear motion may help you to develop red spots at certain interval, and you can reduce the frequency further. And these interfaces, they are rubbing against each other with certain downward force. Now you see that with the passage of time, these red spots, they are getting bigger and bigger. And with the passage of time, the complete interface become red hot. Now you see, this is how a slow motion linear friction welding is happening. So there are so this is some researchers are working in this particular domain also, linear friction welding. So rotary friction welding and linear friction welding. And as I mentioned, this is the mother, these friction welding is a mother process from where the other processes were invented. So this is again a background to, because our intention is to talk about more on a welding. Now, our actual presentation starts from here. Now you see that if you look at the friction stir welding technology, now this friction stir welding technology has been divided into two parts. You have a welding part and you have a processing part. So our first session is more focusing on a different welding technology, friction stir welding technology, followed by a processing part. One of the speaker has already given you a very detailed session on friction stir welding. So I'm not going to repeat that element. And then based on that, we are going to build what are the other variants are there in friction stir welding technology. And in the remaining session, in the second session, our focus will be on a processing side. So let's move further and talk about friction stir welding and its variant. So this is a one which has been explained to you by a speaker from University West. And this is like you can see you require a special tool and pin, and this pin will be inserted tool, then the shoulder makes the contact. Once the shoulder makes the contact, you can apply the feed, and then this type of good quality joint can be developed. So this technology, which has been already explained to you, right? And so the main heart of the friction stir welding lies with the tool. Friction stir welding tool is non-consumable tool, and there are two major elements you have. One is the pin and another one is the shoulder. The pin is pin responsible for mainly for material flow, while the shoulder is responsible for generating the heat. So shoulder is generating around 80% of the heat, while pin is generating around 20% of the heat, because the pin main function is to do mixing of the material at the interface. Before I move further, I would like to explain you one more nomenclature, which is advancing side and the retreating side. Now you see the welding direction arrow and you see the tool rotation arrow. You focus on these two arrows. So both the tangent, the tool rotation tangent and the welding direction tangent, both are coinciding on this side. So this side is called advancing side and the opposite side is called retreating side. So if you say, for example, now it is rotating in a clockwise direction. If you rotate in anti-clockwise direction, right, then what will happen? This side become advancing and this side become retreating. So this is another important thing which you need to consider, because our interest is to talk more about friction stir welding technology for dissimilar metal joining. So moving further, this is what another elementary diagram which may help you to understand that what are the steps involved when you go for a friction stir welding. So the step one is the plunging, shoulder makes the contact and a lot of friction heat will develop, and then you apply the feed, and this is how the joint will develop. So this is the process. And if you spend a little bit more time on metallurgical part, you see the metallurgy under the pin, metallurgy under the shoulder, adjacent to the shoulder and outside the shoulder. So all four sections, under the pin, under the shoulder, adjacent to the shoulder, and then the original parent metal. So they have a different temperature regime. The temperature is maximum under the nugget, followed by the shoulder, followed by the heat affected zone, and then the parent metal. Since the temperatures are also different, there you see the grain refinement is also different. You can see the finest grain under the pin region, followed by the shoulder, followed by the heat affected zone and your parent metal. So this is what a metallurgical understanding about the temperature regime and the grain size under the different region. So when you take a tool, like tool has two different elements, as I mentioned, the pin and the shoulder. Normally we have a cylindrical pin with the threads also, threads with the fluids also, right? And sometimes we can go for even plain shoulder. Normally we go with the plain shoulder, but in the shoulder also you can have some feature, right? So this type of features in the shoulder may help you to improve the material flow also, and it does not allow the material to escape from that particular region in the form of flash or something, right? So this particular features, what you can see here, scroll shoulder, right? This is featureless. You don't have any feature here. This is a plain shoulder, but this type of feature may help you to enhance the material mixing, right? So this is one. Now, so that was a background about friction stir welding. And this is one of the slide why I am showing you this slide, because the one who invented the friction stir welding is here. His name is Dr. Wayne Thomas. He is Wayne Thomas. He is the one who is working with TWI. TWI is the Welding Institute, and this welding institute is in UK. So I had the opportunity to attend one of the 11th FSW conference in Cambridge. That time had opportunity to interact with Mr. Wayne Thomas, the one who invented friction stir welding technology. Now, to begin with, our focus is on friction stir welding of dissimilar metals and materials. Now, to start with, the first part of friction stir welding is dissimilar metal joining. When you say dissimilar metal joining or dissimilar material joining, you are familiar with the conventional parameter which are important in friction stir welding and processing. Say RPM is important, welding speed is important, tool tilt angle is important, downward force is important. At the same time, there are other two parameters which are very important when you talk about friction stir welding of dissimilar metals. One which is called positioning of the material. You see here this slide, whereas it has been written that the hard material will go on advancing side and the soft material will go on retreating side. Say for example, you are talking about aluminum and copper. Now aluminum is soft material, so aluminum can go with the retreating side, while the copper, which is the harder material, will go on advancing side. So this positioning of material is very important. Say for example, if you're working aluminum, copper, no problem, because both materials are same, the metallurgy is same, right? You don't have a difference in thermal property, mechanical property, melting point, all those things are same. But whenever there is a two different material wherein you want to weld them, that time you need to see the hardened material will go on advancing side. So you may have a question that why the hardened material will go on advancing side? Because as I explained you, advancing side is a side wherein the tangent of tool rotation and the tangent of welding direction, I mean, both are coinciding. So temperature is always higher on advancing side compared to retreating side. Around 150 degrees centigrade higher will be on advancing side. So that's the reason you put harder material on advancing side. Another important parameter in friction stir welding of dissimilar metal is the offset. Now, you see this particular diagram wherein the center of the tool and the center of the joint both are matching, right? So, but in case if you have a dissimilar metals like aluminum, copper, you are not supposed to plunge the tool exactly at the center. You are supposed to plunge the tool away from the center. Now you see here, there is a dark circle here. This is nothing but this is your pin, which is more, contact with the hard material is just minimum. While it is 90% is in the soft material. So similarly, here also, you need to focus your pin more towards the softer side. Contact with the harder material should be minimum. So this positioning is called offset, right? So currently, if you see, normally if you go with aluminum, copper, you go with the zero offset. You plunge the tool exactly at the center. But whenever there is a dissimilar metals, you need to plunge the tool more on a softer side, right? The contact with the hardened material should be minimum. This offset method will help you to control the intermetallic formation. So this is what the explanation is given here in the next slide. The pin offset is nothing but is a displacement of the tool from the joint line towards the softer material. And the offset has revealed to be an effective way of solving the most important concern in dissimilar welding, I mean aluminum copper dissimilar welding, is the formation of large intermetallic structures. If you put exactly in the center, you may get a lot of intermetallics. And then the properties like strength, toughness, ductility will be different. But you put the pin more on a softer side, it will help you to reduce the intermetallic formation and it will also help you to improve the joint property. Now you can see here one more diagram. So as I mentioned, the positioning of the material, right, is very, very important because they are dissimilar. So harder material will go on advancing side, the softer material will go on retreating side. At the same time, the positioning of the pin is also very, very important, right? And so you need to optimize. You need to optimize what should be the offset. So you can see here, it's a very simple mathematics you can understand. See, here I have a pin, and say for example, my pin diameter is 6 millimeter. So half of the pin diameter is what? 3 millimeter. So my maximum offset cannot be more than 3 millimeter. If I start with 3 millimeter, the contact with the hard material will be minimum. Then from 3 millimeter, I can move to 2.5, then 2, then 1.5, 1. So that's how my contact with the hard material will go on. And that's how you can play with the different offset and optimize the strength and ductility of the joint. So this is means very, very important parameter when you go for a dissimilar metal joints in friction stir welding. Now you see with more simple diagram, you can see here, there is a aluminum copper. You can see there is a zero offset, right? Exactly centers are matching. But if you want to play with 1 millimeter offset, you see that the joint line is here. And from joint line, you are 1 millimeter away from this joint line. And there you are plunging your tool. So this is called offset. So similarly, depending on the pin diameter, the maximum offset will be half of the pin diameter. And you can see that a lot of copper particles are mixing in the matrix. So final microstructure is nothing but you have a matrix of aluminum wherein you can see a lot of copper particles mixed with the matrix material. Just to make you understand more with one more diagram, you can see here, this is called, say for example, in case of, now, I mentioned to you aluminum copper. When I say aluminum copper, copper is harder. Yes or no, right? But when you say copper and stainless steel, which is harder? Stainless steel is harder, right? So stainless steel is harder, then stainless steel will go on advancing side and copper is a softer. So it will come to retreating side. Now you see your tool is different. I mean, it is now in the copper side only because copper is softer compared to the stainless steel. So now you can start with the zero offset, you can go with 0.6, you can go with 1.6, right? Slowly and gradually you are increasing the contact with the hardened material, and then you can optimize the offset for a given material combination for a given pin dimension. And these offsets will affect, I mean, these different offset value give you different mechanical property, right? So that's very, very important that you need to optimize. So what are the general issues faced by friction stir welding of dissimilar metals? I already mentioned the challenges when you go for a dissimilar metals through a fusion welding. So there are challenges here also. What are those challenges? You have a different material, they have a different mechanical property, they have a different thermal behavior, right? They have a different heat generation and the material flow, right? Which material will go on advancing side, which material will go on retreating side, how you will optimize the tool pin offset. So these are the set of challenges which are there when you go for friction stir welding of dissimilar metals. Hope this concept is clear to all of you. Moving further, now you can see here, this is how your properties also get affected when you change the offset value. So here I have taken the example of aluminum and steel. Now you see the positioning of the offset which has been given. So if you are with this is called zero position. And if you increase, then the contact with the steel goes up. So now you can see here, this is your zero position. Zero position may give you close to 100 megapascal strength, right? And as you go with further increasing, if you go further into deeper and deeper to the iron side, zero point 0.2, zero point 0.4, right? You see it has improved from 100 megapascal, it has moved to around 250 megapascal. Then if you go further 0.4, it has gone down. If you go to 0.6, further gone down. 1 and 2, very fragile joints. You don't have strength. If you go with 0.6, you can see that minor variation in the offset from 0.4 to 0.6 has significantly affected the strength of the joint. So this is through the example I'm trying to explain you that the offset play a very, very important role for a given material combination, and the positioning of material is also very, very important, right? So here, there is one more example, which is quite a different system, which is friction stir welding of metal to plastics. You might have seen in my profile that we are also working in metal plastic joints. I mean, you see, you have a metal, which is aluminum, and the another side is your plastics, which is PP. And you can see such a good joint which has been developed here, right? Very good mixing between metal and plastic. Now you see our offset is 7 millimeter. Now you may be surprised that offset 7 millimeter means what? Now to make you understand, you see here, if you see this is a joint line, and my tool is I'm doing processing kind of thing here because I'm far away from the joint line. You know there is a large difference in the melting point and the mechanical property of metal and plastic. In this case, it is aluminum. So aluminum melting point is 660. I'm doing stirring and mixing here, which leads to the melting of plastics and joining of plastic. You can see my contact with the plastic is very far. Only maybe because of shoulder is bigger, there is some contact with the top material, and material is getting dragged because of shoulder, and it is getting mixed in the region, I mean the top region. So this is called a melting mode because there is no contact. You are not putting the tool because your pin diameter is 6 millimeter. Your pin diameter is 6 millimeter, and you are not even half of the pin diameter, right? You are at 7 millimeter. Then actually half of the pin diameter is called 3 millimeter. You can see there is a good amount of the mixing between metal and plastics. And the third one, which is called mixing mode. I mean, you can see the offset has further gone down to 1.5. Starting from offset of 7 millimeter to 3 millimeter to the 1.5 millimeter. Now you see this is 1.5. You can compare. Here you can see the aluminum and plastic mixing, you can see optimum. Here it has improved further. You can see at some island of aluminum you can see, right? But if you go further, 1.5, I mean, we are very close to the aluminum, very close to the plastic. And then you can see the good amount of, you can see here. So what I wanted to tell you that aluminum and plastic is totally a different system, like aluminum, copper, SS, they are different system. So here also you need to see that which one you will put on advancing side, which one you will put on retreating side, right? In metal and plastic. At the same time, melting, I mean, heat which has been generated in the aluminum side, this is sufficient for joining the plastic with the metal. So So that's the reason there are totally different offset values which has been tried. I told you in case of metal, you go with the half of the pin diameter, right? But here I am describing you that you go even equivalent to the pin diameter. The pin diameter is 6, you are going with 6, you are going half of the pin, you are going even, I mean, exactly one half of the pin radius. So that is 1.5. And the last mode, which is called grooving mode. So you create a groove. I mean, you create a groove in such a way that your plastic and the metal, they go like a joint, I mean, butt joint kind of situation. And then you can play that parameter. So these are the, I mean, these are the macros probably may help you to understand. So melting mode, mixing mode, grooving mode, these terminologies are not there in the open literature. So these terminology we ourselves has worked out based on our experience in working with metal plastic joint. So one is melting mode. Melting mode means what? You are not, I mean, your offset is very high. Then there is a mixing. I mean, that wherein the shoulder makes, I mean, tool pin makes the contact with the plastics and metal. And then the last one is the grooving. So if you see, I mean, the melting and the grooving gives you very good strength, joint efficiency close to 20%, while mixing mode gives you around 14%. And you can see the cross sections. Through the cross section, you can understand a kind of the failure which happens, right? You can see this is a C. C is nothing but the melting mode. Melting mode means what? You are very far from the joint line. You are running the tool only in the aluminum side, which melts the plastics. Similarly, you have a grooving mode. I mean, the A is nothing but the groove, and the B is nothing but the mixing. So this is how this is a work which is being done in metal plastic system as well. And if you see the a little bit of metallurgical part, you can see the macro. And in the macro, you can see this white region is nothing but this is your plastic. I mean, this is your aluminum. And you can see the dark layers are nothing but the plastic which has been mixed with the matrix of aluminum. So that mixing proportion gives you different property, as I mentioned. You can see starting from 14% joint efficiency to 20% joint efficiency. Fine. So just to mention here, for any friction stir welding application, you require a tool. As I mentioned, the tool is the heart of the friction stir welding process, followed by, as I mentioned, the tool is a non-consumable tool and it follows certain design criteria, the length part and the diameter, the thread and the shoulder diameter, and then holding part. So it follows certain dimension, I mean, criteria. Then you can see here a dedicated vertical milling machine, or you can say 3-axis automatic vertical milling machine, which is required to mount the tool. And then you require a fixture also to hold the plates. So in case if you have a vertical milling machine in your laboratory, you can, with the minor change, you can develop this type of tool. You can develop this type of fixture. And with the fixture and tool, you can perform friction stir welding of aluminum or a soft material like aluminum magnesium very easily, right? So this is one part. We work with the ISRO on a RESPOND project for friction stir welding technology development for 1 millimeter, 3 millimeter, 6 millimeter, and 12 millimeter. So we develop various tooling, various process window, and then their mechanical and metallurgical property. And we transferred this development to the Space Application Center. You can see here some pictures of that. I mean, I'm not presenting everything, but just to give you that we can able to weld even 1 millimeter sheet also. You can see this is 1 millimeter sheet which has been welded with on a vertical milling machine. And you can do friction stir spot welding also. We will be discussing that part also subsequently. Fine. So after giving you the background of friction stir welding for dissimilar metal, now the next particular topic in this presentation is assisted friction stir welding. Now you may have a question that why there is a need for having an assisted heating in friction stir welding. So before I explain you, I would like to explain you this process first. So let us understand that you are doing a friction stir welding, and then ahead of the friction stir welding, there is a laser beam. Now assisted heating can be done with any variety of heat source you have. You can use even arc also. I mean, you can use gas tungsten arc welding torch. You can use even plasma also because they are non-consumable. I mean, they have non-consumable electrode. At the same time, so you can use TIG, you can use plasma, you can even use laser, you can use even oxy-fuel gas welding flame also. So there are various heating elements. Even you can go with the induction heating also, ultrasonic assisted heating also. So there are various possibilities. Now these additional heating will help you to soften the material before the tool reaches there. I mean, you can see here that you are moving like this, and because of the laser, and laser you all know, it is not creating any problem in functioning of the tool. So it will preheat the interface. I mean, preheat the interface, it will also preheat the surface before the tool approaches. So the load on the tool, the wear of the tool, right? And material mixing can be further enhanced with the help of additional heating. So there are some additional variants which has been worked out under the assisted heating mode, wherein you can use laser, flame, induction, ultrasound, right? All these kind. So here you can see there is another picture that help you to understand that laser assisted friction stir welding. Friction stir welding of soft material is easy. I mean, you can go with friction stir welding of aluminum, magnesium, right? But friction stir welding of high conductivity materials like copper and friction stir welding of high temperature material, high strength material like steel, stainless steel, nickel, titanium, it is very, very challenging because their strength is very high, their melting point is very high, right? So whatever the tool which you have designed, whatever the tool material which you have selected for aluminum, magnesium may not be suitable for copper. And whatever the tool material which you have used for copper may not be suitable even for steel, stainless steel, titanium, and nickel also. So all the way you require a different tool material, right? And the design also will be different. So in order to reduce that stringent requirement of the tool material and the wear of the tool, load on the tool, there is an additional variant which has been worked out, which is called assisted friction stir welding, wherein the heating can be done before tool reaches. You can supply some extra heat, as you can see in the diagram, with the help of laser, with the help of gas tension arc welding, with the help of plasma, with the help of oxy-fuel flame also. You can see one more picture wherein you can supply assisted. I mean, you have ultrasonic assisted FSW, wherein you are supplying extra ultrasounds, right? So that you can have a better stirring and mixing of the material at the interface. You can generate good quality joint. Now, before I take you to the next variant, now this is the heart of the entire friction stir welding technology. This slide I have taken ditto from the literature, and just to make you understand that you see here that if you look at the x-axis and you look at the y-axis, why friction stir welding of soft material easy and why friction stir welding of high strength material is not easy, right? So if you see here, aluminum, you all know the melting point of aluminum is 660, right? And as the temperature rises, right, you see the strength will go down, right? So within 200 degrees centigrade, right, you see that within 200 degrees centigrade, starting from say 315, I mean 320 megapascal, it has come back to around 100 megapascal, right? Within 250 degrees centigrade. Such a drastic drop in the strength with the rise in the temperature, right? So that helps, that makes the friction stir welding more promising for the soft material like aluminum, magnesium. But if you go with the steel, right, or a iron alloy, you can see the strength maybe close to 400 megapascal. How much temperature you require to, the strength reduction in the strength? You see close to 650, 700 degrees centigrade. You see close to 700 degrees centigrade, the strength will come back to the same level of aluminum. Say here, aluminum is close to 100 megapascal, iron also close to 100 megapascal, but you see the amount of the temperature that you need to generate, right, which is close to 700 megapascal. Now this is something which cannot be achieved easily, right? You can do easily in case of aluminum, magnesium, or a soft material because it is a temperature is just 200 to 50 degrees centigrade. But getting this 600, 650, 700 degrees centigrade, right, through friction stir welding is a challenge. So that's the reason with the additional heating, like additional heating, which we have discussed just now, either with the laser, either with the GTAW, either with the plasma, either with the oxyfuel, either with the induction, either with the ultrasound. You can, it will help you to increase the temperature, and the load on the tool, wear of the tool will reduce. So that's very, very important for this is, I would say. So these factors make it difficult to apply friction stir welding of steel, as you can see in the temperature dependent strength of aluminum. So there is a concept which is called flow strength. So flow strength, this what you are observing, the flow strength, it goes down, drastically goes down in case of aluminum. But the strength, flow strength, I mean, you see it's up to 400 degrees centigrade, it is more or less same. There is no change in the strength. But as you move from 400 to 600 and then around 700 degrees centigrade, you are achieving 100 megapascal. So that's how it is difficult for friction stir welding of steels and other high temperature material is more challenging compared to aluminum. Fine. So in our laboratory also, we have done such a development, friction stir welding with assisted heating with the help of gas tungsten arc welding torch. You can see here, there is a gas tungsten arc welding torch which has been put ahead of the tool and please understand, the purpose of this preheating is not to melt the material. The purpose is to do the preheating. So this preheating will help you to reduce the wear of the tool, load on the tool, right? And this is what you can see, the complete setup wherein you have a vertical milling machine wherein it has been clubbed with the gas tungsten arc welding torch, because shielding gas are also required. And then experiments were performed with the help of assisted heating mode with the GTAW, because tungsten is a non-consumable electrode and the arc is not going to interfere in the while working with FSW. So you can see here very fine rings which you can see here, right? And this onion ring, what you're observing, very difficult to distinguish at this particular parameter. But as your welding speed increases, right? You can see, you can able to distinguish the onion ring. I mean, you can able to measure also. Now you can see here, you can see here, right? So even if you are applying friction stir welding in soft material, I mean assisted heating in soft material like aluminum, right? You can able to increase the welding speed also very high. Means with the assisted heating, we could able to weld 500 millimeter per minute, right? In friction stir welding. But the moment we go to 500 to 800 millimeter per minute, you can see there is a opening in the surface, I mean top surface, and you can see the rough surfaces also. So these are the results, in-house results. And with the, I mean, if you don't apply assisted heating in high temperature material, still you want to apply assisted heating mode in soft material, it will benefit you in terms of higher welding speed. So that was about assisted heating mode in friction stir welding. So heating play a very, very important role. And as I mentioned, you have to understand this particular slide very, very clearly. And that's makes you more, gives you more clarity why friction stir welding of other material is challenging. Moving further into the another variant of friction stir welding, which is called twin stir friction stir welding. Now, this twin stir is nothing but it is the way in arc welding we use two different arc, I mean, tandem kind of thing. You have a two different arc, one is following other, or one is side by side, right? For a different joint configurations. So here also, as you have seen conventional friction stir welding, right? There are many developments are happening here. Now you see, you for a while you try to observe this slide and see that there are various combinations of twin stir technologies which has been presented. Like in arc welding also, you have a two different arc, they go side by side, they go one is following other. Similar arrangement has been made here also in friction stir welding. So twin stir include four different possibilities. One possibility is called twin stir. There are two tools. One is at the top, another one is at the bottom. Second is side by side. I mean, you can see that parallel one. You see here the parallel one. And in all the twin stir technology, both the tools, they are rotating in opposite direction, right? To, I mean, balance the torque. Then another one, so this is called parallel twin stir, right? Because they are parallel. Both the tools are moving parallel. right? The other one called tandem. One is following another. You see, your welding direction is this, and another was backside tool is following the front side tool. And the last one, which is called staggered. Staggered is similar to what you are observing in parallel, but in parallel, you see there is always some unfused area. So in order to do that, right, in order to avoid this, right, staggered, you see staggered means what? There is some amount of overlap between the two tools together, right? So a lot of interest has been there in parallel, twin stir technology also. And when you look at the research articles, you realize limited articles are available in the area of twin stir technique. So this is, you can see the, cross section wherein you earlier you were getting, there is a unfused area here, but now with this staggered one. So these are the few twin stir technology. Before I move on to this, I have a small clip and I request please confirm whether the clip is visible to you or not.
Yes, sir. Yes, sir.
Okay, okay. Now, so here there is a twin stir technology clip. You can see two tools, right? One is at the top, another one is at the bottom. So as I mentioned in twin stir, there are many possibilities. This is one of them. This is the back side, from the bottom side, because you have a two tool, one is at the top, one is at the bottom. This is the bottom side, top side. So this is called twin stir for, when you want to go with higher section thickness, right? You can, or you want to weld wider area. So this is twin stir. This is one of the type. So now you can go back to the previous slide. You see what the video which you have seen is this. Similarly, you can have, parallel twin stir also, staggered also, and tandem also. So with the one spindle, you can rotate two tools. You have a one spindle. With that spindle, you have one conventional tool, and that conventional tool with the gear, it has been attached with the another tool. So you can rotate the another tool. One spindle will help you to rotate two tools. So going further, there is another possibility in friction stir welding, which is called bobbin tool friction stir welding. Conventional friction stir welding, you are all familiar now, wherein you have a one pin and one shoulder. But here you have a two shoulder. Now you can see here, you can see this is one pin, one shoulder, but here you have two shoulders, right? Now these two shoulders, what is the benefit of second shoulder? Normally in friction stir welding, you require a strong backing. You have to support your aluminum plates or welding plates with the strong backing. Now, why the strong backing is required? Because there is a large amount of the Z-axis forces. You can see here, there are different forces which has been mentioned. One is called downward force, which is called Z, and the one which is with reference to the welding direction, and the one perpendicular to the tool, right? So this downward force, right, is very high. So in order to withstand that, you require a strong backing below the plate. So that strong backing makes friction stir welding applications slightly challenging in some areas. So they come out with the new element, which is called bobbin tool. You're all familiar with the term bobbin. So here you can see here in this diagram, you can see there are two shoulders are there. So tool is not penetrating from the top side, it is penetrating from the side. And the normal case also, your pin is lower than pin length is less than the plate thickness. If your plate thickness is 6 millimeter, the pin length will be 5.8, 5.9. So here also similarly, if your plate thickness is 6 millimeter, the pin length will be 5.8, 5.9, so that the sufficient friction will be generated between the surfaces. And then you're able to weld. So this will solve the problem of the backing requirement. That's how it is called bobbin tool friction stir welding. Your fixture is also different. You see, this is your conventional fixture for friction stir welding. This is your bobbin tool fixture, wherein you have the half of the half plate will be on this side, another half is from this side, and tool will penetrate from this area. Because tool is not, because you have a second shoulder, so it cannot penetrate from the top side. It has to penetrate from the side. So you can see one more picture here. You see, this is how the conventional FSW works, and this is how bobbin tool friction stir welding works. So it will penetrate from the side, and then it will do. You see the second shoulder. Now here you can see the second shoulder. Now second shoulder is the one who is acting as a backing plate. Now here also I have a small clip, probably which may help you to understand the bobbin tool welding easily. This is called floating. Floating means it will adjust during the process. You can see here there is a curvature surface, right? Since it is adjustable, it is called, there are two types of bobbin, fixed one and floating one. So this is floating one, so it will adjust during the process. Now you see this, the bobbin tool, you see the second shoulder, it is penetrating from the side, not from the top. So once it penetrates, so in normal FSW, you are getting a keyhole at the end, but here you are getting a little bit of slot. You see here, there is a small slot which is formed, right? Because you cannot exit the way you exit in FSW, right? So this is called bobbin tool friction stir welding. Probably one more is there to make you more clear about bobbin tool. On floating bobbin tool friction stir welding, you see here that was on a curvature surface.
Welding using zero downforce has been successfully demonstrated at TWI, simply with a traditional milling machine. The technique uses a floating bobbin-shaped tool. Successful demonstrations have shown that FSW can be performed using traditional, unmodified machine tools. A milling machine like this is all you need. The technique is ideal for joining low-temperature softening materials such as aluminium. Here, grade 6082 aluminium is being joined. The bobbin tool penetrates the joint line either directly or, as in this case, from a milled recess in the material's edge. The process lends itself to joining closed sections, where conventional use of a well-supported backing bar is either difficult or impossible. Since, by definition, the bobbin creates a full penetration weld, the potential for creating kissing bonds, usually associated with lack of tool penetration, is eliminated. The process uses a one-piece tool, unlike some FSW variants, which require complex multi-piece tooling. As the machine bed is traversed, the material passes between the shoulders of the bobbin. So the process involves zero vertical force, unlike earlier adaptations of the friction stir welding process. No backing bar is required because the bottom shoulder supports the underside of the weld. Since the bobbin tool is free to move up and down throughout the welding operation, it naturally takes up a vertical position where the top and bottom shoulder forces are equal. This feature also compensates for any misalignment between the tool and the material. Laboratory trials have shown that the bobbin variant of the FSW process creates very little distortion. This is because the rotating tool creates a symmetrical heat input throughout the weld section.
So this is
Well,
about
to learn more
bobbin
about
tool.
bobbin welding,
So that's how, with the help of additional shoulder, it will help you to support the backing requirement, and you can make the process suitable for many other applications. So this is the cross section which you can see. which is for bobbin tool friction stir welding. You can see the onion ring pattern, right, which is there here, even here also, right? So this is under the pin part and the shoulder part region, thermomechanically affected zone. Then you have a advancing side, rotating side, those things. Fine. The another important technique which is called dual rotation. Dual rotation, there is another way, means you have a pin and shoulder. There is another variant in friction stir welding. It's called dual rotation. The dual rotation means what? A pin and shoulder, they are independent to rotate, right? They can rotate in same direction also. They can rotate in opposite direction also, right? So that's how it will help you. Means the purpose is to reduce the, minimize the heat input, because shoulder generates a lot of heat. 80% of the heat is being generated through the shoulder. So if you wish to reduce the shoulder movement, right? So that's how you can helps you to control the heat input control through the dual rotation technique. So this is one way which is called dual rotation. And they can rotate in same direction also, in opposite direction also, and with the different speed also. Now, moving further, there is another variant of friction stir welding, which is called friction stir spot welding. The way we talked about resistance spot welding, arc spot welding, tick spot, mid spot, right? There are many riveted joints are there, right? Similarly, here also, compared to, compared to conventional welding processes, through the friction stir welding, through the same machine, you can do friction stir spot welding also. So we'll first talk about conventional friction stir spot welding, followed by some variant which has been written here called refill friction stir spot welding, pinless and double-sided also. So this is your standard friction stir spot welding. What will happen during the process? So you have a pin, you have a shoulder. There is a pin, there is a shoulder. So you rotate and then you plunge it. It has been supported like a backing or an anvil, you can say. And this pin, it's penetrate beyond the interface. You can see here there are two plates and it is mainly for lap configuration. So the pin has to penetrate beyond the interface level, right? You can see the interface between the two sheets here, right? So this pin length should be such that, or your parameter should be such that it should cross the interface, right? And then once you eject, you left with the keyhole, the way you are getting a keyhole in normal friction stir welding. So here you don't have a feed motion. You just rotate, plunge it, and then eject it, right? So you don't have a transverse motion the way it happens in conventional, because you don't want to weld throughout the length. You are welding at one particular spot only. That's the reason it is called friction stir spot welding. But the challenge is what? You have a keyhole. Now you have an open hole here, right? So which may give you a little bit of less strength compared to the filled one. So the researchers are trying that how you can avoid this type of cavity at the end of friction stir spot welding or at the end of friction stir welding also. So you always left with small cavity here. So this cavity is not at all acceptable for many engineering applications. So with that reference, they are investigating some or other process. So this is a color picture of friction stir spot welding, which you have seen in earlier with the line diagram. You see there is a tool and there are two sheets are there, and the tool has to penetrate beyond the interface. And then when you eject, you left with the, this type of hole. You can see here, this is called exit hole. Similar hole you are getting even in normal friction stir welding also. Now you can see here, if you compare the earlier picture, you have seen there is a exit hole, there is a cavity here. But now you see the another picture. Can you see any cavity here? No, there is no cavity here. It is filled one. So how can you achieve that, right? Without adding filler metal, without adding the filler metal, with the addition of the own material, right? You can fill the cavity. So the new process which is being worked out, which is called refill friction stir spot welding. Now, there are two variants are there. One which is called shoulder plunge, another one which is called probe plunge. Please listen this critically and look at the arrows which has been given here. So we'll discuss both of them one by one. And you see that the whole intention of refill friction stir welding means what? They want to avoid this type of keyhole, right? Or exit hole. So you can see the yellow color one is nothing but your pin, and blue one is nothing but the shoulder. And then the green one is nothing but the clamp, right? So initially what will happen? What will happen? The shoulder arrows and the pin both are moving towards the workpiece. See, there is a workpiece here, right? They are in the lap configuration. And in the second stage, what will happen? the shoulder is moving down, the pin is going up. You can see the motion is opposite, right? The clamp remain in the same situation. The whole intention of the green is to clamp the sheets, right? So they will remain the same. But in the stage 2, you see the shoulder is moving down, the pin is going up. You can see the deformed material. Can you see the deformed material here, right? Because since the shoulder is going down, the material is deforming, and that material is, pushing in the upward direction. After some time, this shoulder is going up and the probe is going down, and you can see whatever that deformed material which was pushing upward, now with the help of probe, you are pushing back. And then finally, both shoulder and probe both are moving up along with the clamping. So since it has been run through the shoulder part, it is termed as shoulder plunge variant. And the another one, which is called a probe plunge variant, wherein you can see a similar situation, but instead of shoulder driven deformation, here it is pin driven deformation. So let us understand this part also. First stage is same in both the case, right? Here your shoulders were moving down because shoulder has to deform the material, right? But in this case, what is happening? Pin is deforming the material. You see that the pin is going down and the shoulder is going up, completely opposite to the stage 2 here, right? And then in the stage 3, it is opposite to this one. The shoulder was going, pin is going up, shoulders are going down, right? You can see the deformation at the interface, and you can see here also, and finally the joint. So this is called refill friction stir spot welding. So here also, for understanding, I have a small clip for all of you. Yeah, let me show if can. This is very, very important now. Now you see the shoulders are going down. Now you see first clamp. So the most important element probably is this. See, let me show you. Now you see here, this is what you can see. This is the gray one, the bigger one, they are nothing but they are the clamp. The central one is nothing but the probe or pin, you can say. This is the shoulder, right? So in this case, it is the shoulder driven deformation. The shoulders are going down. And since the shoulders are going down, you see the material is deforming. Temperature is rising, material is deforming, right? So this deformed material is going up. And then the moment get reverse. Now pin will go down and the shoulder will go up, right? So that is what, and you can see the temperature regimes also. You see close to 427 degrees centigrade in this. This is the interface of two sheets, which you can see here stage 1, and you see this is all are at the same level, right? So that's all. Fine. Moving further, this is called here also the purpose is same. Why they have developed pinless friction stir spot welding? Because they don't want that hole which is forming at the end. So because they know that hole, why you are getting a hole? Because that hole is because of the pin. So if you remove the pin, is it possible to weld? Yes, it is possible to weld. So they remove the pin and then they come out with a process called pinless friction stir spot weld. Only the shoulder, it is there to deform the material, and then you can see, but you can see there is a large deformation, right? A deformation is very high, right? Because you are deforming not with the pin, you are deforming with the shoulder, and you can certainly avoid the exit hole, but the overall deformation is very large at the joint location. So this is called pinless friction stir spot welding. So earlier one was a refill friction stir spot welding. This is called pinless friction stir spot welding. And before that, what we discussed is a conventional friction stir spot welding. Then researchers are also trying to explore a double-sided, the way we talked about twin stir friction stir welding, that is double-sided friction stir spot welding is also there, right? So you can see here, there are two shoulders are there, right? Because here also they are both, I mean, pinless only. You can see two shoulders are there, but there is no pin. Both the shoulders are coming, right? They are deforming the material of respective side. And then you can see the deformation pattern. And finally you retract, you will get the joint. So this is called double-sided friction stir spot welding, but again, it is pinless. There is no pin here, right? So not conventional friction stir spot welding with one shoulder, double-sided friction stir spot welding, right? With the two shoulder. And as you know, friction stir spot welding has wide applications in automobile industries, right? Spot welding is extensively used. Just to mention here, resistance spot welding is extensively used in automobile industry, in car body. Probably in one car body, you have around 2,000 to 5,000 resistance spot welded joints. So research now industries are exploring how friction stir spot welding, especially refill friction stir spot welding, can be used for variety of these applications. And as I mentioned, you can have a various kind of the shoulder instead of in especially when you are going with the pinless. Please understand, when you are going with the pinless friction stirs spot welding, it is essential that you should have a proper material mixing. So how will you ensure that? If you go with a not plain shoulder, then you get a different kind of material mixing. But if you have a shoulder with the different type of features, you see the features are different, right? Scroll shoulder with the different features, right? This will help you to promote the mixing at the interface, even if you don't have pin, right? This is a conventional tool used in friction stir welding, right? But they are for steel application, but this you can see the pinless. And hope you understood that this pinless friction stir spot welding, wherein your shoulder has an important role to play. It has to play the role for material mixing also. It has to play the role for heat generation also. Fine. So after discussing this friction stir spot welding and its variant, second last process is friction stir scribe welding. Another novel process. Very limited work is been reported in this particular domain as well, wherein you can see normally when you go for a friction, and just to mention here, this process is suitable for lab configuration, right? The way friction stir spot welding also it is for lab configuration. This is also for lab configuration. Lab means what? You can see this joint configuration, right? So in normal friction stir welding, when you go for a lab configuration, the tool is penetrating through the second plate, and then you will get the weld, right? But there is a new process which is called, with the conventional friction stir welding tool also you can do lab configuration, no problem. But then the pin length should be according to the both the plate thickness. But in order to reduce the deformation of both the plates, they come out with the new concept, which is called scriber. You can see here, there is a scriber here, right? You can see in the diagram also, there is a scriber. You can see here also, there is a scriber. So this process, which is called friction stir scribe welding. So scriber, we are all familiar with the term scriber we use in workshop. There is a scriber, it will, for generating, for before cutting, with the scriber, we do the marking. So you see there is a scriber which is attached to the pin. You have only pin. Now the pin is penetrating through the first plate. You see when you have a lab configuration, so pin has to penetrate through the first plate. Now for the second part, for the second plate, right, you have a scribe. Now scriber is there, right, which will, actually cutting the material at the interface. So say for example, you are going with polymer and metal. Your polymer will be on the top, metal will be at the bottom. So this scriber welding is another important process. This may be, welded one also. It may be a single piece also. You can have a single scriber also, double scriber also, triple scriber also, right? So there are many variants are there in friction stir scribe welding as well. Now you can see more closer view when you are done with the welding. This is your schematic diagram wherein low melting point material will be at the top, high melting point material will be at the bottom. So when you do the scribe welding, and if you look at the cross section, this is called hook. It is, this hook which is nothing but of bottom material. They are trying to grip, right? They are trying to grip the material which you have at the top. Stitching. It will do exactly stitching of the top material. So the moment pin penetrates, because pin is penetrating up to the top layer, then the scriber is generating this type of hook and it will grip the top material. So let me show you a small clip to make you understand the process. Friction stir scribe welding. See the scriber here. You can have a multiple scriber also. Single scriber, double scriber, triple scriber. And create very good joint. Now we see the mechanism. So initially you require some kind of pilot hole. So because otherwise the load will come on scriber and the scriber may get damaged. Scribe welding extensively used for reported, but still at research level. Mainly for lab temperatures. You see the researchers are exploring the possibility of friction stir scribe welding for highly dissimilar metals, metal polymer with the straight scriber, with the tilted scriber, right? So that is there. And before I close this session, I have a last process to explain you. That is called stationary shoulder, another process under the category of friction stir welding, which is called stationary shoulder friction stir welding. As I mentioned, that you are not rotating. We talked about dual rotation. Dual rotation means what? Both are rotating, right? They can rotate in same direction also, they can rotate in opposite direction also, and you can control the RPM of pin and shoulder independently also. So here the stationary shoulder means what? You are rotating only the pin while your shoulder is stationary. There are few applications wherein you want to reduce the heat input drastically, right? Say for example, for storage of electronics housing in the magnesium based material, especially for aerospace applications, satellite applications, right? You don't want to put too much heat of friction stir welding to those electronics component, right? So that time you can go with the friction stir welding, stationary shoulder friction stir welding, and there are many other applications also. The whole process is very novel process, right? And let me show you a small clip on this. Stationary shoulder FSW. So that means the shoulder is not going to rotate. It will just there on the surface to provide you the downward force, right? And you will get a very smooth, almost polish surface. You can see the heavy duty robotic system. You can observe this clip carefully so that you can understand the shoulder is not rotating, only the pin is rotating. Now you see the pin has penetrated. You might have seen that initially has shown that electronics housing or a cover kind of thing. application. Now you see it has penetrated, right? And then it is following the path. You see the shoulder is not rotating. Shoulder is there to give you the downward force, right? And the kind of the finish which you are getting is excellent, almost polished surface kind of thing with the minimum cross section. So this process so as I mentioned, after the development of friction stir welding, the mother process is friction welding, and from there, friction stir welding has been developed. And from the friction stir welding, there are many variants. So we started with the friction stir welding for dissimilar metal combinations, dissimilar material combinations. We talked about assisted heating part. We also talked about twin stir technology. We talked about friction stir spot welding and its variant, and friction stir scribe welding, and lastly, this is friction stir stationary shoulder FSW. So with this, I have come to an end of my talk. And so thank you all the participants for patiently hearing the talk. Probably in case if you have questions, probably we can take towards the end of the second lecture also. Or if required, if you have anybody has any quick question, we can quickly take one or two questions.
Yeah, thank you, sir, for the wonderful session. It was certainly covering a wide gamut of processes under the stir and rather the friction stir umbrella. Sir, some quick questions, sir. There is one participant asking how much plate thickness can be welded with twin stir?
Okay, with the help of twin stir, as such, there is no report which talks about what thickness you can weld. But according to my knowledge, with the conventional FSW, you can weld even up to 75 millimeter thick plate. The twin stir, the whole intention of the twin stir is to cover the wide area. I mean, for shipbuilding applications, if you see shipbuilding applications wherein you want to weld a large area. So as such, thickness may not be a issue, but it also depends that you are talking about which material. If you say soft material, naturally you can weld, according to my knowledge, I have seen around 10 to 12 millimeter thick plates through the twin stir technology.
Okay, sir. Sir, and I think we'll take one more, and then the other questions, maybe as you suggested, could be at the end of the
Yeah.
second session. Sir, could you give some suggestions on the effect of offset for
Hmm.
varying thickness, FSW, Taylor
Effect of
welded blanks?
offset on.
Offset for varying thickness, FSW.
Okay, okay. So when you have a varying thickness, there also, if the varying two different, say one which is of say 3 millimeter, maybe other one maybe of say 5 millimeter. So one is 3, one is 5. There are various thicknesses. So there, the offset is as such for dissimilar thicknesses, the offset is not required. So only the positioning of material is very, very important. If they are of the same material, I mean, say for example, you have aluminum and you have aluminum, but only the difference is in the thickness, right? So, I mean, the one with the higher thickness will go on one side of the tool, and the one will go on the retreating side of the tool. I mean, advancing side and the retreating side. So when you have a different thicknesses of the same material, uh, the higher the thickness, it will go on, I mean, advancing side, the other one will come on the retreating side.
Right, sir. So I do request the participants that the other questions would be taken in the second session, which is the session after the current session.
So do they have more questions?
Yes, sir. There are a couple of questions.
Okay, okay. So, so kindly, if possible, please keep a track of those questions so that we can help them out with those answers also. And because
And sir, if you
otherwise,
don't mind, I think it's a small question. If we
please,
can
please,
talk.
please.
Yeah.
Yeah, yeah.
Sir, may I know the amount of force or pressure applied during FSW?
Yeah, so the downward force, which is what you are applying during the friction stir welding of aluminum, because the material has to specify. So because that downward force value will be different for different material, even for it will vary. Initially, the downward force is very high. I mean, when the plunging happens, during the plunging stage, the downward force is very high. Once the plunging is over and the shoulder makes the movement, then downward force gets stabilized. And then while ejecting, it will further go down. But for soft material, it is what we have observed in our laboratory. It can go close to 150 to 200 kg downward force in Z direction.
Okay, sir. Sir, the next question asks, what are some of the applications of metal to plastic joints?
Okay. Mainly in automobile and aerospace applications, researchers are exploring the metal, steel, metal plastic joints, or even friction stir welding of plastic is also explored by many researchers, mainly automobile industries.
Right, sir. I do request participants to please hold your questions for the next session because the questions are, coming up. So the last question, is there any advanced computational model which predict and mitigate residual stresses in FSW joints?
Residual stresses, online monitoring kind of thing.
Uh, is there any advanced computer models which can predict and mitigate residual stresses?
I don't have idea. I need to check. I don't have idea on that, whether residual stresses can be monitored, and it can be measured. Residual stresses anyway we can measure with the various techniques like other technique, but for specific to this, I'm not aware of that part.
Sir, once again, we'd like to thank you for the wonderful
Thank you.
session.
Thank
Yes,
you.
sir. And we again look forward to hear
Sure,
in the
sure.
next session. Yeah.
Thank you.
Thank you, sir. Over to you, Manoj, sir.
Okay, thank you, sir. Am I audible?
Yes, sir.
Yes.
Okay, thank you, Dr. Kunal Mehta, sir, for chairing the session. So once again, I would like to thank Professor Vishwesh Badika, sir, for his insightful and engaging session on advanced welding technology. I think your expertise and deep knowledge in this field have truly enriched our understanding, sir. Thank you once again, sir.
Thank you.
So now I would like to invite Ms. Kritika Gupta from National Institute of Technology, Kurukshetra, to introduce our next speaker, Dr. Vishal Ashok Vankade, sir, Assistant Professor at the Indian Institute of Management, Bodh Gaya. Kritika, madam, are you there?
Hello,
Hello.
am I audible?
Yeah, you are audible, please.
Good afternoon, everyone. My name is Kritika Gupta from NIT Kurukshetra, a research scholar. To continue with our session, it is my pleasure to invite our next distinguished speaker, Dr. Vishal Ashok Vankade, Assistant Professor at IIM Bodh Gaya. Dr. Vankade is currently serving in the Department of Operational Management and Quantitative Techniques at IIM Bodh Gaya since July 2023. Before this, he contributed significantly as an assistant professor in the Department of Mechanical Engineering and previously in the Department of Industrial Engineering at Pandit Deendayal Energy University, Gandhinagar, Gujarat. He earned his PhD in Industry 4.0 from the National Institute of Technology, Tiruchirappalli in 2022. His academic journey also includes an MTech in Cloud Manufacturing 2016 and BTech in Mechanical Engineering in 2014. Dr. Wankade's academic excellence has been recognized with the prestigious Budding Researcher Award for his doctoral work in 2022, along with an academic proficiency prize during his MTech at NIT Trichy. His research contributions are commendable, with over 50 peer reviewed articles and book chapters, accumulating over 1400 citations and an impressive H index of 20. He is an active member of professional bodies like Institute of Engineers India and American Society of Mechanical Engineers. His primary area of research include Industry 4.0, smart manufacturing, additive manufacturing, circular economy, advanced manufacturing processes, optimization, and multi-criteria decision making. So today Dr. Vishal Ashok Wankhede will enlighten us on the topic Smart Manufacturing Industry 4.0. Let us warmly welcome Dr. Vishal Wankhede to deliver his talk.
Okay. Am I audible, sir?
Yes, yes, Dr. Vishal, you are
Yeah.
audible.
Okay. Okay. Yeah. Thank you, Miss Kritika, for such wonderful introduction. And I also would like to thank the Professor Vishwesh Badega, sir, and Professor Manoj, sir, for inviting me uh, in this talk to contribute my whatever knowledge I have regarding Industry 4.0. So, sir, shall I share my screen?
Please, please.
Okay.
Yeah, it is
With my
visible.
yeah.
Yes,
Okay.
yes,
Okay. I'll
visible. You
just
can
make
make
it.
it full.
Yeah.
Yeah,
Yes. Yes.
yeah, done, set.
Yes. Okay. 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 So, welcome to all the participants for this ATAL FDP program, uh, Smart Manufacturing and Digital Transformation Industry 4.0, organized by Department of Mathematics and Department of Mechanical Engineering, Pandit Dindal Energy University, Gandhinagar. I'll be delivering a talk on smart manufacturing. So, first, I have already extended my gratitude to Professor Badeka sir and Professor Manoj sir. Along with that, I'll also hello. Yeah, I also like to extend my gratitude to the entire PDU management for inviting me for this talk. So, since I understood that you all will have already gone through the what basics of Industry 4.0 is, and along with how Industry 4.0 is useful in manufacturing, I'll be taking the entire session with blend of informative as well as some of the application points which can be there in manufacturing industries. So, my entire outline would be introduction followed by how Industry 4.0 is observed globally, what other countries are doing, and how they have made their action plan. Followed by smart manufacturing, what basically the smartness is there in manufacturing, along with what modern technologies which you already have uh, introduced, and along with the industrial policy, what industries are uh, uh, going for this Industry 4.0. And then I'll be discussing with how today's factory looks like and what tomorrow's factory we are aiming for, what exactly we are looking transformation into manufacturing industries, followed by some of the examples and the what government of India is taking as an initiatives for uh, making this adoption process smooth, followed by some applications and research. So once again, this entire talk will be so informative. So any kind of questions or queries if you have, kindly put into the chat. I'll be happy to address it at the end of this session. So to begin with this talk, so I just want to ask what smart is basically. If anyone can just put in the chat or can unmute your mic and say what exactly smart do you mean? Because smart nowadays is looking like a word which people are applying everywhere. Whatever device or whatever uh, you name as a process, the smart, the moment they apply, they aim for something else. So what is that keyword? So if anyone can highlight what is smart according to you. So I'm not able to see the chat. If I request coordinator to let me know if anyone replies to this.
I request the attendee, they can unmute themselves and then they can answer if anybody would like to answer.
Yeah, please unmute. What is smart according to you? Okay, fine. Can anyone highlight the key aspect from this image? What exactly you see here, or what is not visible here?
Actually, sir, it's a vehicle
Hmm.
manufacturing assembly line, and which are
Okay.
to be equipped with different robots.
Yes. Very good. So basically, the smart, which was my previous question. So whenever we talk about smartness in manufacturing or in any processes, we are actually eliminating humans here. So if you see this image itself says that hardly there is a human, or even if human is present, he might be in the control phase or probably into the monitoring side somewhere else. But the entire manufacturing line, if you see, is automated by robots. Correct. So the smartness, when we say into manufacturing, we are actually calling it as a smart manufacturing. So which in depth the definition goes different as per the standards. But yes, whenever we talk about smart, we are expecting an operations or any process to work itself or to take decision by itself. So this is what smartness, what we are expecting into manufacturing. So another question is what makes then manufacturing smart? So what exactly we are expecting? So here if you see, now whenever we talk about a manufacturing factory, so we want that entire industry or a factory to use the technologies of Industry 4.0 to automate or to take decisions based on the predictive analytics. Second, to whatever benefits we are going to get is nothing but creating transparencies, then optimizing processes, connecting and collaborations, and then finally operational agilities. So this in depth we can understand, we can realize only uh, when we think on how Industry 4.0 technologies can be implemented. Which implementation of Industry 4.0 you had already a session where Industry 4.0 implementation you might have studied in some particular process. But this is what the benefit which we get, and this entire benefits are nothing but makes a manufacturing smart, or where we can say that now the actual manufacturing industry is moving towards smartness. So what is the foundation for this? We call it as an industrial revolution. Now whenever we realize some changes in industries or in the whatever surrounding we have, so we call it as a revolution, right? So when do we say that there are changes, or in which sector we are observing changes in uh, industries, and then we say that yeah, there's an industrial revolution. So whenever there are major changes in, the very first is industry and services, like the way we make, buy, or sell things. Second, the transportation, the way we travel, and the society, the way we live. So here we are now observing these changes. We have completely transformed. We are basically we say it at that we are living into Industry 4.0. So we have seen that how the entire services of a particular product is being changed, and we are experiencing it. We are observing that how people are now selling it, how people are buying it, what customization options are available with us. Similarly, we have also seen the transportation mode and the society where we are. We are fully surrounded by digitalization nowadays, and we can see that now it becomes a part of our life. So it is usually a new ways of thinking and doing and new technologies that cause the changes to happen. So this is basically the industrial revolution when we see changes in this three arena. Now, this you already seen that what first industrial revolution to fourth industrial revolution. So here I just wanted to highlight a point where you can see the degree of complexity what it takes to implement this industrial revolution. So initially, whenever the first industrial revolution have started, which was the degree of complexity was less, was not much. No doubt at that point of time it was though difficult, but now if you think on as the centuries are passing and we are moving towards industrialization, so we are actually expecting complexity in entire completely transforming the fourth industrial revolution, or completely moving towards fourth industrial revolution because of the evolution of 5.0 as well. So we are still experiencing it, that I'll talk later. So this is how the entire journey started from Industry 4.0, and now we are into Industry 4.0. Now, let us see the journey so far. What developments uh, have occurred in USA, Europe, or any other countries which are into manufacturing side. So what exactly they have seen? So if you talk about the USA, which who is actually giving a strong focus on innovation and technology. So the technical hubs or the technological hub, what they are now moving towards AI, IoT, robotics for the industrial application. You might have seen the applications what previous speakers have talked about manufacturing, and you have also observed the robotics, how it is playing an important role when we see with respect to developments in technology. Similarly, the government of US they have also took some initiatives with respect to advanced manufacturing like NNMI, that is National Network for Manufacturing Innovation, and the Manufacturing USA program. And several companies, including majority is automotive and aerospace sector, because see, automotive sector is the one who are ready to adopt any, or they are ready to adopt whenever there's a new technology or any new initiatives is coming in. So whatever experiment or anything to be done for industry with respect to implementation of technology, then automotive and aerospace sector is the one where people are mostly trying for it. Similarly, we'll also see that how technologies are adopting here, and they have adopted this industry 4.0 principle as such to improve their production process and product quality. Follow this again, the second country, which is China, has also made a substantial investment in Industry 4.0, and where they are running the campaign, which is Made in China 2025, which they aim to transform the entire China into high-tech manufacturing hub with involvement of AI, robotics, and IoT. They're also working on building smart factories, intelligent supply chain, which is a need of the hour. Supply chain, which we know that how difficult is to uh, at when we think before, if we think without digitalization, a supply chain we can definitely may not be able to fulfill the customer demands what they have. But this intelligent supply chains are now making uh, possible each and everything about with respect to customer satisfaction. Same, the China's technologies have also trying to develop their own semiconductors or chip, and so that they can be self-reliant in the critical technology. So now they are able to move ahead because of adoption of Industry 4.0, what China is also now focusing on. Similarly, Germany, as you might be knowing that the Industry 4.0 is basically the evolution of it. The word itself came from Germany, because Germany being the largest manufacturing hub, where we say that all advanced manufacturing you will observe in Germany itself. So Industry 4.0 being their own concept, they are committed to advanced manufacturing, and where SMEs, where if I talk about Indian SMEs, there's still research challenges. People are still working on how Industry 4.0 can be adopted in Indian SMEs, where the research is still going on, which I'll talk at the last. Uh, but in Germany, they are SMEs is basically playing a significant role in developing their economy, and this SMEs have already adopted this Industry 4.0 technologies, and to stay competitive and innovative. So Germany is the one which is particularly for the what we say manufacturing side. Yeah. Similarly, France is also coming up with their own initiative, that is Industry 4.0 for future. What if you see the French, uh, they have their campaign name, but it means that Industry 4.0 for future. So they are also aiming to modernize the industrial sector, and they have also formed the clusters like Paris Cyclic Cluster and the Lyon-based Aerospace Valley, where they are aiming to foster this R&D in Industry 4.0 technology. Now, so these are some of a few major countries who have started this. Here in this map. You can say that there are other countries as well which have started investing in Industry 4.0, being a recent developed concept which was in 2011. This concept was initially started with Germany, but then followed by each and every uh, country have started adopted it by naming it in a different form. On a similar line, Indian government is also trying to foster this. They have already have a action plan for how Industry 4.0 can be implemented in each and every sector. So here also, if we have focus on this, so China, if you see, they have already into now second phase of Industry 4.0, and they are planning to go for up to 2049, where they want that each and every industry to be completely Industry 4.0 driven, and it should be recognized as one of the global what is a facilitator for each and every manufacturing sector. Even they have associated Industry 4.0 along with the economy, and this is what the target what other countries have with respect to Industry 4.0 uh, implementation. On the other side, if you see USA, France, Germany, UK, China, Australia, Spain, Italy, they have their own plan for Industry 4.0. But the moment when we say Japan, uh, basically there's an history for Japan. What Japan believes in humans. Japan is mostly talking about quality initiatives. So where people started with Industry 4.0, Japan started talking about the what do you say quality 4.0. So here Japan is coming up with the concept of Society 5.0, and they have already developed a plan with respect to implementation of Industry 4.0, but not eliminating the societal part. So this is what one of the uh, learnings from Japan what world can take. So they have recently started the Society 5.0, where now people are talking about Industry 5.0 as well. Okay. So similar, if you talk about developments or the journey so far, the Japan and what market share they have captured at present, what they have, and this is what the value the in billion euros what they have earned by adopting the Industry 4.0. So here, if you see the largest manufacturer in terms of machinery manufacturing, where they have the economy of 563 billion euros in 2011, what they had. Similarly, if you talk about Germany, as I already said, they are the main for known for manufacturing, so they are the largest exporter. Similarly, Russia, who is the machinery manufacturing, but they are at the fourth largest, along with the USA, Europe, same automation side. So this is some data what can which can motivate our country to understand what Industry 4.0 is to the in global perspective. Similarly, as I said that industry policy funding initiatives also we should know, where I have also discussed regarding India. So what China did, China is now when strategic industries point, if you see how they are developing this. So they have this new generation information technologies, high-end equipment manufacturing. These are some of the initiatives what they are taking to build strategic industries. The investment they have made like up to 2015, they had this 1.2 trillion euros, which uh, they have right now. It's par up to like they have highly invested into these technologies. Same if you see in machine tool sectors along with IT sectors or IoT development, this China is having their own policies. Similar European Union, if we say they also now coming up with this ARTEIM, which is Advanced Research and Technologies in Embedded Intelligent Systems. So where they have invested almost 2.4 billion euros. And similarly, they have other initiatives and funding for Industry 4.0 to make it successful. Coming to India, if you talk about our country, so we have had a 5-year plan since 2012 to 17, where which led to increase in public and private R&D investment. Similarly, cyber physical system innovation project that also we launched to conduct research into humanoid robotics. So therein the research aspect into robotics into manufacturing is going through this initiatives. And this Bosch Center is there for research in CPS, which I'll discuss like how many centers India have, which focuses specifically on Industry 4.0. And this also we established in 2011. So here we can see that as the Industry 4.0 concept came, we also started developing such initiatives for adoption of Industry 4.0. Okay. Now, so obviously we can't achieve now when since we have seen that what Industry 4.0 is important, how globally it is taking care, so India as well. So there is no doubt that we can't achieve the smartness in manufacturing without embracing the modern technologies. So what we can do? So how what basically smart manufacturing represent? So here only three important factors what is required, that is automation, second is operations information, and advanced analytics. So these three key factors are responsible for making entire manufacturing smart, and these factors link machines through open platforms and enable to think or react in real time. So there's no doubt if I replace this automation word with real time automation, which can make the manufacturing uh, smart. So similarly, if you see what NIST said, so NIST defined smart manufacturing as fully integrated, collaborative manufacturing system that responds in real time to meet changing demands and conditions in the factory, in the supply network, and in the customer needs. So the key points, if we see, we want our entire machines or any process should be fully integrated, they should be collaborative, and they should respond in real time. And why so? Because now since the customers, the Industry 4.0 provided a lot of options to customers, as well as the supply chain is the way we modified, the way we narrowed down it, so that customer can take the benefit of whatever product is coming into market. So smart manufacturing being fully integrated and collaborative will certainly help in responding the changing demand what customer has right now. So this is what NIST defined the smart manufacturing, and uh, this is what we are trying to achieve for each and every industry. Okay. So what modern technologies are required? As you might have seen this, starting from you say autonomous robots, simulation, system integrations, which is horizontal and vertical integration, industrial IoT, cyber security, cloud, additive manufacturing, augmented reality, and big data. Now, Uh, if you talk about what technology is important at present, so I would rather say that cybersecurity is the one which is the need of the hour to implement when industry is going for implementing any one of these technologies, because cybersecurity is the one, since we always say that data is a new oil, and the entire manufacturing uh, uh, industries or industry 4.0 technologies are trying to focus on implementing each technologies one by one. No industries have actually implemented all the technologies, or they may be implementing one or two technologies parallelly, but implementing all the technologies need the cyber security brings a major concern, because we can see the kind of attacks what this system has right now. So the cloud cybersecurity being an important for this modern technologies that makes an entire manufacturing smart. Okay, so this is one more one again we can see that applications which based on each and every technology. So here when we talk about advanced robotics, so any manufacturing process or any system which works on human based, or wherever that there are definitely chances of error. But when we expect the advanced robotics which can take decision by themselves and which is integrated fully with sensors, so there we name it as an advanced robotics. Additive manufacturing, you might have seen 3D printing being one of the first technology. So there also we have seen that how additive manufacturing is helping to go for completely replacement instead of completely replacing the machine uh, through just replacing a part or prototype. So this is also one of the major technologies what additive manufacturing brings in. So decentralizing 3D facilities to reduce the transport distance and inventory. This talks about the real-time or remote monitoring of additive manufacturing, which is there in Industry 4.0, which can be possible through Industry 4.0, where we connect the data and you'll get the additive manufacturing importance from remote perspective. Same augmented, along with it, there's one more terminology that is virtual reality, which we are using to realize the experience or the real experience for industry uh, for any product. So when we talk about augmented reality, it is basically used for maintenance or the logistics or all kind of SOPs what they have. Same simulation or horizontal or vertical integration, industrial internet, cloud, cybersecurity, and big data analytics. So these are some the technologies which refers to Industry 4.0 and which is also help to make manufacturing smart. So remember, Industry 4.0 is a technology which can be applied in any domain. When it applies to manufacturing, we call it as a smart manufacturing. So it started with the cyber physical system, which if you see this infographics, what I have, so cyber physical system talks about there's a cyber space and we have a physical space. So cyberspace, when we are actually talking about communication, control, and computation. So these are the three layers which brings in the information about the system, and then we can monitor it, and further we can take decision based on the analysis what the system brings in. So here, when we talk about physical space and cyberspace, we say it as a cyber physical system. Similarly, we have a big data analytics. So whatever data generated from the manufacturing, the data itself, previously there was no doubt there was a data, people were using the process, but the data was not, we were not recording it or we are not able to capture it on a larger scale. So since now we have a data, a huge data is generated through any operation, so you can take decisions with respect to cost reduction, with respect to any new products or services, or any decisions which can lead to a faster analysis that can be done using the big data analytics. Then we have Internet of Things. There might be some confusion between what cyber physical system and Internet of Things does. Basically, Internet of Things is a subset of cyber physical system. When we talk about cyber physical system, we are connecting the entire industries with the cyberspace, wherein Internet of Things is basically where each and every device in industry is connected with the internet and the operations is being monitored virtually to take the decisions or to take the better decisions, right? So this Internet of Thing is also one of the important technology for real-time monitoring or automation purpose. Additive manufacturing, you have already understood how it works, what is the process, basically how this additive manufacturing contributes or help us to realize what green manufacturing is. So I'll not talk much on this, but additive manufacturing now, since this was the manufacturing which started with automation, now we are moving one step ahead to make this manufacturing into a real-time automation process, because this is one of the process which also drives through a circular economy, which is also one of the objective to go for Industry 4.0. So additive manufacturing is also one of the important technology for Industry 4.0, which can help industries to make a green manufacturing. AR, VR, that is augmented reality and virtual reality. So whenever we assigned what is it, fully immersive experience, we call it as a virtual reality. And this augmented reality is, as I said, that you will use another device to use, like you can see here. So this basically talks about the augmented reality part. So in manufacturing, the industries are using to for maintenance purpose. So even the Bosch is also they have also implemented augmented reality for workers training as well as for uh, maintenance of manufacturing machines. So they have implemented this augmented reality, one of the what do you say the technologies which can be used for embracing Industry 4.0. Now, so after discussing this technologies, so this is some if I put all the technologies into the manufacturing industry and show you a simulation, so this is how it will look like where suppose this is an assembly line where and you can see that each part is connected via a wireless network, okay, and even we can observe that very less human workforce is available, that is only for probably for monitoring or just to uh, a recording purpose, but the decisions are being taken only by the machines. Okay, the robotic is here. The robotics will take a decision with respect to manufacturing or with respect to completion or with respect to defects, whatever it has. The what is it? The control, and same the edge computing is also applied here where the decisions being transferred and finally uh, you will get the product whatever you have. So robots are also they have used to transfer, so hardly so real time effect we can see here when we see any manufacturing industries. Similarly, we can observe here how the real world and we are connecting to the cyber world. So real world, when we say we have a local communication, we have a human, you have an environment, machine, product, and so on. But the moment we bring in the digitalization, the entire path, if you see, is connected to the network, which where the data is stored, and this cyber world is held by for the cyber world is now connected to social machines, smart products, augmented operators, virtual production, and through global facilities. So this we can see that we are now moving towards economies of scale when we actually implement Industry 4.0 or when we connect into these all technologies into an industry. So this is one of the product processing or production system for smart manufacturing. Now, moving toward this, what we have seen is first we just observed why Industry 4.0 is important. With respect to we have seen what globally Industry 4.0 is going through, what other countries are taking initiatives to embrace Industry 4.0, and what India is having a plan. The detailed plan I'll explain towards the end, but what exactly Industry 4.0 have is important. Now we'll see what we are targeting when we say that we want to build a smart factory, smart manufacturing. There are allied technologies, there are allied concepts such as you have smart cities, which is again towards another sector. Same. So as I initially introduced that smart manufacturing, the smartness word which we have that is associated with real-time operations. Okay, so real-time automation. So only automation is not a part because sensors are already developed in Industry 3.0. We are now moving towards micro sensors and so on. So that's why we need uh, we can now achieve the real-time automations and we can which can certainly help in improving the efficiency. So what today's factory is basically we have the rigidly sequenced car manufacture which is on the production line, correct? Here there is no scope of any customization. So there's no scope of any changes. Or if I put in this way, if I want to replace any part of any other organization of any other machine, I cannot substitute here because that flexibility is not allowed uh, with this rigidly sequenced production line what we have. Because the production line you may put up, you may set up, and what you say, um, uh, uh, different uh, parts or you may assemble it. So whatever the position part or the respective area is there, that only we can go ahead with this and finally you can achieve. But so that's what even whatever you do, but individuality is not encouraged in today's factory, and as a result, it is not possible to incorporate in individual customer request, which may request you to to include an element from another product and so on. For example, to fit a Volkswagen with a Porsche seat. So that is not possible with today's automotive. However, we are aiming to build a factory or a manufacturing which can be customized. As one of the example, we know that additive manufacturing is the one which talks about this, but still we are aiming for this manufacturing which is decoupled, fully flexible and highly integrated manufacturing system where an individual customer's requirement also can be achieved. So here, this is one of the target which we can achieve when we implement Industry 4.0 uh, technologies in an assembly line. So this is one which we are aiming. So what parameters or what aspects we are looking for when we move from traditional industries to Industry 4.0 industries or Industry 4.0 factories? The very first is we are now moving towards automation and robotics instead of manual labor intensive process. We are also looking for control aspect where previously it was what traditional factory do is centralized decision making, and we are moving towards decentralized. Basically, whatever data we have, based on that, we want to take a decision system. Or decentralized means wherever you are, you can take up or you can control that particular activity or task. Similarly, connectivity we are also looking for, which where we are talking about interoperability or interconnectivity through IoT and data sharing, and also the batch sizes, maintenance part where we are now moving for predictive maintenance with the help of sensor, customization. As already said that we have limited customization opportunities because of the inflexibility what is associated with today's factory, but tomorrow's we are looking for highly customizable products. Same, you have data utilization or remote control. Similarly, the energy efficiency point or sustainability point, which is one of the most important nature. See, whatever today's factory is doing, Industry 4.0, though we are talking more on Industry 4.0 implementation, somewhere there should be a discussion around sustainability where how the disposal of this electronic waste will be. Whether because this part is also one of the important part, which is one of the research area what people are now focusing on, or researchers are talking about the sustainability point with respect to Industry 4.0. So these are some of the aspects which we are looking or which we are expecting to achieve when we move from traditional factories to Industry 4.0 factories. Okay. So just to discuss this, I have a video where we which can talk about the dark factory scenario. So I'll just see. So you can see this is the future plant. Any human is involved in this. However, they can visualize each and everything on the screen, and they can also visualize all the operations remotely. The entire site, which is network, and this network not only locally but also globally. So the similar nature was local, what was the local factory had, the same is globally available, so that's what the remote manufacturing. Yeah. So here we have seen that how industry, what factory is expecting with implementation of Industry 4.0. So all operations, manufacturing operations, basically towards the productivity point of view, wherein the production planning you take all the operations which is very close to customer. That is, uh, we are trying to optimize it. So similar kind of example you can find from Adidas, who is, as we all know, that it's a global sports brand and has been running its mass customization program, which is MI Adidas, right, for several years. So this, they are also now coming up with a product which allows customer to personalize or customize their sports footwear to meet their performance or styling needs. So this is also one of the initiatives what they're taking since several years, and uh, now they are trying to embed advanced technologies that reduce the need for workers, which are the key drivers behind the strategies. And same, they are also now trying to embed the running shoe sole manufactured using 3D printing technologies. So this is also one of the initiative by MI Adidas, which they have already started adopting Industry 4.0, and they want customer to, uh, the entire idea is to fulfill the customer needs what they have. Okay. So if we say what technologies we want for any organization which can lead to smart working, so the very first is remote monitoring of production, then remote operations of production, augmented reality for maintenance, then virtual reality for workers training, and the both, which is we also call it as a mixed reality, that is for product development and collaborative robots. So here, this is what if technology, any technology, if implemented into organization, can help us to achieve this many aspects or these many what do you say functions, right? So these are some of the technologies what we can see. Similarly, in from research point of view, as I already said that research is still going on for Industry 4.0, that too from techno managerial point of view. So where people are still talking about how Industry 4.0 can be implemented, what could be the implementation patterns, or how manufacturing can adopt, or what technologies they should adopt, what kind of foundation technology they should have, and so on. So this is one of the research findings which I would like to, I thought like which can be helpful to understand, which is from a very reputed journal, which is IJPE. And what for each technologies or for each function, they have mentioned what exactly technologies and organization need. Like vertical integration, they are expecting to have PLCs, SCADA system, MES, ERP, machine-to-machine communication, and so on. Similarly, for virtualization, so AI for predictive maintenance, AI for planning of productions, and so when you talk about automation, so robots, which almost most of the industries have started transforming their industry into robotics. Traceability, then flexibility, and energy management. So these are some of the categories and the technologies which are required to make Industry 4.0 smooth implementation in industries. Okay, this is one more. The same, the authors have tried to provide the complexity aspect of each and every technology. So here you can see this particular arrow talks about the complexity level, where it has three stages, where if which can be implemented stage wise into industries and can help in understanding the implementation pattern, wherein these are the front end technologies which is required to achieve this. So here, the when we talk about smart manufacturing, which is our area of concern, so which can be stage one, there should be a vertical integration. These are the technologies which should be there, followed by energy management, and then traceability, which is traceability of final products. Now, with this, what we can achieve is smart products, smart working, smart supply chain, right? Same for automation too, that is stage. We have automation and virtualization. These are some of the application area where for maintenance or virtual commissioning or industrial robots and so on. These technologies we have already seen. This is the framework what they have suggested, and they have clubbed together how at which stage these technologies should be used. And finally, we have a flexibilization where flexible lines or additive manufacturing can be introduced into the organization. And here you can see these are some base technologies which are required, which is cloud, Internet of Things, big data, and analytics. So the complexity levels increases as we move towards each and every function, right? So, for example, flexibilization to make an industry flexible is much complex. This is finally the outcome where if we start with the base, which is ERP, MES, SCADA, and so on. Okay. Again, this is with respect to IoT, that is Internet of Things. So if you see the manufacturing facility, here also we can see that hardly any humans are available, and what they have done. So they have monitored the entire production flow in real time just to eliminate the wasted time and reduce in-process inventory. So in manufacturing operations, waste defines times. Basically, when we say waste, so we are not talking about here any physical waste. We are not talking about any physical waste in terms of the prime importance is given to the time which is wasted. So this concept is much earlier, not the part of Industry 4.0, but yes, Industry 4.0 will help in achieving the reduced time. So same, you can see that implement condition-based maintenance alert. So these are some of the functions what we can make. Same aggregate product data and process data analysis to identify constraints. RFID sensors can be introduced. And same here, production line, what it has, it will trigger it, right? So this entire operation, if it gets success at locally, so globally now people can manage it remotely using sensors or limit to conserve energy and reduced cost. So this is how we can reduce the cost, along with the we can achieve the sustainability point what it has. Okay. So one more video I have, which is for smart manufacturing. A little, the timing is little more, but I'll just introduce you a few key points from this video.
Manufacturing is vital to the U.S. economy in general and maintaining our strong economic growth.
As a manufacturing organization, we constantly face cost pressure on our products. There's also a regulatory scrutiny to ensure that we maintain the quality of our products.
We need to be able to communicate to our suppliers, communicate to our customers, exchange data back and forth. All that's going to be based on cloud technology.
Smart manufacturing allows manufacturing companies to optimize their production and supply networks through bringing together islands of information.
Smart manufacturing, which is really about enabling that latest IT infrastructure to support manufacturing, is really vital, cost competitive on a global basis.
I've been at Pfizer for 34 years, and this is one of the most important manufacturing technology breakthroughs that I've seen during that time.
Manufacturing stands on the brink of a new industrial revolution. While the last revolution was powered by engineering innovation, this one is driven by unprecedented access to data. These new revolutionary advances merge both physical and virtual worlds, opening doors to completely new areas of innovation, making manufacturing far more cost-effective, efficient, sustainable, and safe. But smart manufacturing faces significant challenges too, requiring a new IT infrastructure that all U.S. manufacturers and suppliers can access and contribute to while maintaining their individual security and proprietary systems. The potential for smart manufacturing to drive new business opportunities and create new jobs is so compelling that leaders from many organizations are working together to make it a reality.
At General Mills, we're looking for smart manufacturing to solve a number of problems. We have a project that today solves a supply chain issue from field to fork. It looks like it's going to cost about $10 million. It's going to take us about 2 years to execute. What I'd be looking for is for smart manufacturing to change the scale of that in an order of magnitude. Instead of $10 million, $1 million. Instead of 18 months, do it in a couple months.
Smart manufacturing is powered by the development of new tools that allow manufacturers to make better use of data.
Smart manufacturing is making something with that data. So understanding it, looking for the correlations between different data points, and using that information to make intelligence, which allow us to control our processes, but also to predict what's going to happen and manage that to be able to optimize those processes.
Advancements in sensor technologies also play a role by making it possible for manufacturers to create cyber-physical systems.
The role of smart manufacturing in collaborative cyber-physical systems is to really bring together people, process, data, and things. And it's enabled by the emerging Internet of Things technologies.
Using low-cost sensors, cyber-physical systems monitor and collect data from manufacturing processes. These systems enable the physical world to merge with the virtual world, opening the door to innovative business solutions. Smart manufacturing allows companies to synthesize information in ways that have never been done before, creating a connected enterprise.
Connected enterprise is about bringing together information that exists in a plant floor with information that exists in business systems and tying that together with the supply chain to optimize your production and the overall supply network.
The challenge is each system independently has its own methodology of doing things. So in a smart manufacturing methodology, we would be able to connect these things together. We would have maps to do these things. We'd be able to solve complicated problems.
Pfizer is using smart manufacturing to develop remotely controlled processes, virtual laboratories, to ensure a consistent supply of products globally. Pfizer has also created portable manufacturing platforms using similar concepts, allowing them to efficiently produce vaccines for children in the countries where they're needed most.
One of our focus areas is develop small scale, modular, flexible versions of our larger manufacturing technologies. An example of that is right behind me. Smart manufacturing is really important to us in developing the control strategies for those manufacturing technologies and also in helping us to effectively deploy them throughout the world.
What really needs to happen to move smart manufacturing forward, to move this open platform forward, is we have to invest in developing the technology of open that all of us can play in, the vendors, the companies, so that we can enable this aspirational vision of smart manufacturing for small, medium, and large companies.
The Smart Manufacturing Leadership Coalition is helping to do exactly that. SMLC supports public-private partnerships with the sole purpose of raising and advancing a smart manufacturing infrastructure throughout the U.S.
At Pfizer, we realize that we can't make smart manufacturing happen on our own. We need investment and support from other pharmaceutical companies and from the academic institutions that help us develop these technologies.
And that's what's so exciting about smart manufacturing, is we're bringing together a coalition of people, a coalition of resources to tackle a problem that has been too large for any one vendor, any one company to solve by themselves. Participate with us, join with us, invest with us, and get us to this common open platform that allows us to interact our businesses together.
Smart Manufacturing Leadership Coalition, building infrastructure.
Okay, so we have seen that how smart manufacturing is basically is embedded into industries. This video clearly talks about the one of the focus industry, which is healthcare industry, where they have they want because it works on the no error product. So any and even the demand to fulfill the customer demands, right? So there we have seen that how what exactly they want to connect the entire the people and the data together. So they want to build up the open platforms where everyone can enter and everyone can play an important role in uh, what is a decentralizing the system. So for followed to this, this is one article which I find where uh, there are some challenges what Industry 4.0 has with respect to its implementation. So a survey has been done where they identified that unclear economic benefits where because the excessive investment what it has, so that is one of the challenge what Industry 4.0 brings in, and that's why in India the SMEs, which is currently the researchers are working on this specifically implementation of Industry 4.0 technologies. Now the technological focus is going on instead of implementing or moving entire industry into Industry 4.0. Similarly, the second is the skill opportunity, that is skill-based uh, qualification which employees have. So that uh, this is another second challenges, followed by the lack of standards because implementing any technology is not enough with respect to what is a uh, with respect to the huge investment what it incurs, but however the sustainable it should sustain for a longer period. So standards is not yet defined for implementation of Industry 4.0. That is one of another challenge. There's no legal situation. There's a very low maturity level of required technologies what it says. So these are some of the challenges which people face with respect to implementation of Industry 4.0 in industries. Okay. Now, after discussing challenges, what Industry 4.0 or what action plan India is taking to foster its adoption in with respect to smart manufacturing. So basically, CII, that is Confederation of Indian Industries, they are the one who is suggesting about how smart manufacturing can be taken ahead. So since government of India's target for manufacturing and the Make in India initiative which it has uh, is to grow the contribution of the sector from 390 billion USD to 1 trillion by 2025, uh, which translates to a growth of 12% per year. And this can be achieved only when we move towards smart manufacturing. That is what the CII talks. But what smart manufacturing needs? It needs basic training and the skill development. As we just don't want technologies to get embedded, but also the sustainability part. We want it should also take care of the environment and as well as the workers should have enough understanding on how this technology can be built or how these technologies can be taken care. So with this, what India has done, we have a 4 center of excellence, which is Kirloskar Center for Learning in Industry 4.0 is in Pune, then in IIT Delhi, then Industry 4.0 India at ISC Factory, it is Bangalore, and then Smart Manufacturing, that is CMTI Bangalore. So these are 4 centers of excellence what India has. And what we need to see is basically perils or the positives. We do have reasons for not transitioning to smart, but also we have some positive or the benefits. So here the focus is basically towards the micro. If you see, we have opportunity for mass customization and also have opportunities for increased quality, productivity, speed, and security aspect if we go for this, right? So this is what they have. If they are moving towards it because of this thing, which is fear of becoming irrelevant, because the one who don't adopt it, they will become irrelevant into the market. So this is what an industry needs to think on. Okay. So benefits, yes, we already know that Industry 4.0 have enough what is a capabilities to work on cost reduction along with the production time. So whatever productivity aspects is there in manufacturing, we are talking about which is time and uh, uh, cost. So here also we can see that uh, basically the Varroc is one of the industry that experiences approx 20% improvement in their efficiency because of adopting smart manufacturing, and also 5% decrease in the defect rate, like that's a product defect. Similarly, Boss also achieved 30% decrease in the production time and cost reduction of 3.6% per annum. Right. So this is what the benefits what at present the smart manufacturing. These are there's no what do you say from large enterprises. They are experiencing a technological base because technology wise they have implemented it. What CII did till now, so their action plan which they already had. So they have the step one suggested that identified all the relevant stakeholders who can help in uh, what is it in foster in implementing this industry 4.0. They have already defined smart manufacturing, and they have prioritized the sectors that can promote smart manufacturing. Right now, this critical step which is yet to be implemented, which to develop Industry 4.0 India platform, which based on this and research is still going on how best what could be the best framework or strategy uh, to create Industry 4.0 in country. So similarly, to develop an enabling ecosystem for fostering adoption of smart manufacturing, this is one of the ongoing process. So this recommendations already given by the CII, and they have already provided it, but we are yet to implement this. But these three have already done. This one of the most important sector is automotive and the healthcare. So where smart manufacturing can be realized, right? So these are the sectors which I said automotive, which is one of the where 45% of the Indian manufacturing sectors are experiencing smart manufacturing, and being the one of the most uh, uh, they're always at forefront in adopting such technologies when it comes to improvement in productivity. And same information communication, if you see this manufacturing, so this is again the electronics industry, and this is mother sector for all smart hardware such as sensors. They they uh, they they are the one who will be who will be helping manufacturing sector to promote smart manufacturing. Same engineering sector is also one targeted one, and then MSMEs. So MSMEs is uh, uh, this again contributes to 45% of our this Indian manufacturing, and they are biggest employer after. So these four sectors they CI have targeted. They asked to start implementing industry smart manufacturing from this. So till now, whatever we have seen, so what makes a smart manufacturing enterprise? So as simple, it just you have an equipment, you have an intelligence that you need to transfer to a cyberspace, right? With interconnectivity in between, data will be generated, and this data will be helpful in taking decisions. So this concept is given by Andrew, who is known to be the one who introduced the smart manufacturing. So smart manufacturing is in general it means that just to implement it to implement a technology which can take a faster decision. Okay. Coming to application point of view, so predictive analytics, asset management, safety operations, efficient and productive process. These are the common functions what smart industries has. So inside factory, if you see this, these are some of the applications what you can find if we implement Internet of Things, that is industrial Internet of Things. The very first is saving energy, then preventive breakdowns by tracking the what do you say the runtime, then predict equipment failure before it happens, that is predictive analytics, then diagnose process constraints, then quality, then improve response, understand how your product perform in the hands of customers through IoT embedded. Then this will definitely help in realizing what kind of modifications to be done, which mostly done by the market analytics, but this can be done using IIoT if we implement it into the products. Similarly, it will also help in improving this OEE, that is overall equipment effectiveness, where we talk about availability, performance, and quality. So these are the three parameters which talks about how to completely utilize the time, that is your planned production time. If a manufacturing product is consuming, for example, an hour, so not entire time it utilize, some of the time get wasted. So that's why if you see the available time was very less, the performance was though okay, quality though okay, but your overall equipment effectiveness was not that much high. So though you have taken care of the quality, though you have taken care of the performance of your machine, but still your OE. So this track of OE can be done using Industry 4.0 technologies, or the one of the technology which we already know, that is ML, AI, ML. So can be used to real-time tracking, and industries have implemented it. They have created a dashboard and they are monitoring this parameters and OE key, how best we can achieve it. Because having 80-90% is good enough to utilize the time what it has. Same in maintenance, we can use. So, like if you install and sensors on the equipment, uh, you can real-time data gets into the system, apply AI ML to predict the machine future, it gets the requirement, and finally automatically schedule the maintenance task. So this can be done using AI or the technology of Industry 4.0 for from maintenance aspect. So these are the some maintenance. I have considered only one application, that is maintenance part. So here we are targeting the prescriptive maintenance, where ML help you to predict the failures and identify the solution itself. So we are targeting this. We are still into this, where we are trying to predict the failures. Failures are still rectified by the humans, but yes, we are trying to achieve the lower MTBF and MTTR, so that we are higher MTBF, lower MTTR, so that we are trying to achieve it. Yes. The one more application is with respect to smart supply chain. So that supply chain, as I already said, that the smartness associated with any one of the keywords, so that becomes your intelligent supply chain. So that also we are trying to apply, where it starting from the pre-configuration and testing part, then integration with respect to software, and then your the package are loaded, and finally entire package is connected to the digital, where we also digitalize the operations of real-time inventory reporting, material management, or any reverse logistic is applied here, so that can be easily get into supply chain. So these are the future, basically not yet implemented, but this is the future which we want. One more application is seen in article, that is cyber physical machine tool, which is replacing your CNC machine tool, where it just want to develop a cyber twin, that is your digital twin. So digital twin is nothing but you will just create a virtual product of physical one, and you will monitor it into the same parameters in which it works, and whatever failure it occurs, or whatever wear it occur, whatever the physical situation may occur with that particular tool, can be realized into the cyber twin, and such things can be controlled when you run into physical part. So they have definitely taken some help of the sensors, which data acquisition devices, where they collected the data. So this is one more application which I have seen, that is machine tool cyber twin, that is with respect to Industry 4.0. Okay. Now, then future of smart manufacturing is basically we need digitalization, then increased reliance on modeling optimization, material product process, enterprise dichotomy, then resource sharing, and so on, then cybersecurity and safety. So this is what we have, where we are expecting the smartness into manufacturing completely. Okay. Now we'll see one video, a short video again, to explain the the practical aspect of Industry 4.0 with a short story.
Do you own a manufacturing plant, or do you manage a manufacturing plant? Do you face some production problems and look for a simple and effective solution for them? Do you want to adapt your plant to Industry 4.0 for less production cost, better quality products, shorter production cycles, more efficiency at every production level? If you do, let's hear Steve's story. He used to manage factory trouble. There were a lot of problems in factory trouble, causing disruptions on production line, delayed delivery, therefore causing unnecessary expenses. What kinds of problems were these? Steve could not monitor the production line. Were the machines in production now, or were they in standby? Was the production completed or needed to be in progress? How much time is required for a job order? Steve didn't know these issues exactly and couldn't get accurate data from the documents. There was no notification when a machine stopped working frequently or when a breakdown occurred in production. It took some time until the problem was noticed, so machine and equipment efficiency could not be estimated. Steve couldn't estimate his employees' efficiency. He didn't know whether they worked efficiently during their shifts or they were causing disruptions. He didn't even know if their breaks took longer than it should be. There was no real-time data for stock movements. Sometimes this could result in a total mess. One day, Steve met Meta Smart Factory. They presented to him one single, efficient, and the smartest solution to overcome these problems. Steve accepted immediately. Their team set and installed their products to every machine, and they installed their application to Steve's computer and Steve's phone. Now, Steve can monitor all production flow from his computer. He can plan job orders. He can manage all production processes accurately. He can even follow these using his mobile phone when he's at home or when he's on vacation. When a machine breaks down, Steve and his maintenance team get notified immediately. Following that, the team can respond to the failure by arranging a repair process. Steve knows when the machine starts working. Now, there is no more mess in warehouses. How many products or supplies are there in warehouses? How many of them will be transferred? All stock transfers can be monitored and managed by batch management of Meta applications. Every break of employees are recorded to the system. After a workday, or at the end of the week, or after a month, the efficiency of employees can be analyzed by a request. A report attached to a graph is generated, so Steve can interpret his employees' efficiency. In addition to this report, Steve can analyze his manufacturing workstations, machine status on those workstations, production orders, overall equipment effectiveness, and more. In this way, Steve can get a lot of estimations about the delivery, costs, and also he can decide maintenance times of machines to increase productivity. Steve solved his production problems with the best solution of Meta Smart Factory. Factory trouble turned into factory ever active. The productivity and profit of Steve's plant increased significantly, and Steve got the edge over his competitors. Well, what is Meta Smart Factory? It is an
Okay, so this is what we have seen the uh, the applications where how the industries, basically third party, is helping industries to uh, adopt Industry 4.0 technologies. But yes, they have to first implement technologies, and then only they can be able to capture this entire data. So now, coming to my last point of discussion, which is research aspect. So I'll just talk about how where Industry 4.0 is moving now. Now there's enough research on implementation of Industry 4.0, but right now people are now researchers are now moving towards integration of such aspects. So I'll be just talking about how this Industry 4.0 is linked with circular economy. So since we know that circular economy is nothing but your the disposal pattern. The linear economy is nothing but you take a product, you use it, and then you dispose it. That's it. The disposal strategy could be your incineration mode. Either you'll burn it or you may landfill it. Right. The circular economy says whenever you have a product, instead of after using it, instead of disposing it, you try to reuse it, remanufacture it, refurbish it, recycle it, and so that it can be again entered into the manufacturing system, and not to use the natural resources what it has, because the product do takes materials which are not having much, which are having a good recycling rate percentage. So this circular economy can be integrated with Industry 4.0 technologies so that Industry 4.0 sustainability can be improved. So this is one of the research going on. So those who are interested can discuss with me more if you want to know more on circular economy, how it is integrated. Similarly, as I said, Japanese are more talking about uh, uh, their concept is from lean, quality, Six Sigma, and so on. So if we integrate Industry 4.0 with this, for example, the concept from lean, if you take like foolproofing is one of the concept. If we take that is Pokayoke and integrate with the IoT, which is your Internet of Things, can be achieved. So lean and Industry 4.0 can be achieved, and then Six Sigma, whatever you have, because it's based on the purely data, and to take decisions based on the uh, what is it, the process it has, and it aims for improving the process. So if you integrate with AI ML, so definitely the organization can take better decision on this. So this is also one of the growing research area where people are talking about. This is one most recent transition industry, which is human collaboration. What I believe is Industry 4.0, what researcher felt is it's ignoring humans somewhere because technology is entering into picture, so humans are not involved here. So 5.0 is nothing but bringing back human into this. So how human can be collaborated with the machines, and where we can again take help of this technology. So this transition pattern they are still studying. As I said, Industry 4.0, uh, we are still experiencing it. We have not yet completely achieved. And this is one of the revolution which we have experienced. We realized it after what do you say? We introduced it first, and then we started experiencing it. So this is the one which we have. More focus is now going giving on worker safety. So where how AI, how AR, VR, that is augmented and virtual reality can be embedded into worker safety, and how this can be helpful. So this is also one of the research which is going on. And then performance measurement, as and when the technology is introduced or implemented. So performance of that technology is again uh, going to be measured. So these are some of the key research area where Industry 4.0 aspect is going on from academics or researchers point of view. But yes, industries are still uh, struggling to implement it, especially SMEs. So if anyone wants to really work on the research, so kindly focus on Industry 4.0 and SMEs, which is still a growing area for research. Okay. So with this, I stop my presentation, and I'll be happy to take questions from you. So any discussion you have or anything if you want to ask, kindly either you can unmute it or you can put into the chat. Okay. So if anyone have any questions, can ask, or any discussion if you want to make with respect to this. Yes, definitely smart manufacturing, as I said, is still industries are experiencing it. So if anyone wants to have any questions.
Yeah, participants can unmute themselves and they can ask the questions one by one. Kritika ma'am, you can take that questions.
Yes, sir. In the chat box, there are no questions.
So yeah, there are no questions. I can see some answers. Yeah, I appreciate this. I think I asked about what is smart. Yes. So
If
anyways, if you
anybody
have
has
any
some questions, they
questions,
can ask.
yeah. If you have questions, you can ask, else you can write to me on my email ID. Anything, if you have, you can certainly drop me a mail. I've shared my email ID in the chat box. So if you have any queries or anything you want to discuss with me with respect to its implementation, you can certainly discuss. Okay, Manoj
Okay,
sir,
sir. Thank you.
Kritika, yeah, I think there are no
Yes,
questions.
sir.
Yeah,
Okay.
okay,
There are no questions till now. If
okay.
anybody have some questions, they will mail to you. So thank you,
Sure,
sir,
sure.
for the enlightening session on Smart Manufacturing Industry 4.0. Your
Thank
expertise
you.
and in-depth knowledge of have provided us valuable insights into involving landscape of smart manufacturing and digital transformation. We truly appreciate the time and effort you invested in sharing our knowledge to us. Thank you, sir, once again.
Thank you, Kritika. Thank you, sir. Thank you, Vadega sir.
Sir,
Thank you, Manoj sir.
just a minute, sir.
Yeah,
I
yeah,
now
yeah,
request
yes,
all
yes.
the delegates to please switch on their video so that we can click the common photographs with sir. Dharmik?
Yes, sir. I take
Yeah,
the photographs.
please, you can do that. Yeah, sure.
Sir.
Okay, thank you, thank you. Thank you, Miss Kritika Gupta, madam, for giving your valuable time and sharing the session.
It's so. Thank you, sir.
Thank you, Vishal
Thank you, sir,
sir.
for the
Thank you.
opportunity.
Thank you.
Thank you,
Thank you, sir.
Vishal sir, for sharing the in-depth knowledge on Smart Manufacturing Industry 4.0 and accepting our request. Thank you once again,
Thank
sir.
you, sir.
Thank you. Thank you so
Thank you,
much,
sir.
sir.
Thank you, Krunal
Now
sir.
I would, sir, thank you.
Yeah. Okay.
Now I
Bye,
would
sir.
like to invite, bye, sir. Bye.
Shall I leave?
Now, yeah, please, sir. You want to say
Okay.
something,
Okay.
sir?
No, may I leave now? So,
Okay,
Thank you, Vishal sir. Thank you.
okay. Okay.
Thank you, Vishal
Thank you.
sir.
Thank
Thank
you,
you
sir.
so much,
Thank
sir.
you, sir.
Thank you.
Thank you, sir. Thank you.
Now, moving ahead, I would now like to invite Ms. Shruti Rathore, Assistant Professor at LDRP Institute of Technology and Research, Gandhinagar, Gujarat, to introduce our next speaker, Professor Vishwesh Badeka, sir.
I think Dr. Manoj, because this is on the same day, same speaker,
Yeah,
probably
but still
I
a
think
minute,
we,
sir.
yeah, probably we can save that time and help for more questions. Maybe a little bit, you can say, let her, I mean,
Yeah, sure. Just a minute, not more than
sure,
that,
sure.
sir. Thank you, sir. Thank you so much. Shruti ma'am, are you there?
Yes, sir. Am I audible?
Yeah, please. Yeah, you are audible, please.
Thank you, sir. I would now like to invite Professor Visis Badeka, sir, again to continue his session on advanced welding technology. Taking no more time, I'm again uh, telling sir, please look forward to your session. Please, sir.
Sure, sure, sure. Fine, fine. Thank you very much. And again, welcome back. I think we want some break or we can start now immediately. Means participants want some 2-3 minutes break or okay. Right. So good evening, everyone, and welcome to this second presentation of the day, which is on advanced welding technology 2. And I would be focusing on friction stir processing. And to begin with, I would like to mention here that in the first session, we talked about friction stir welding technology. And as I mentioned, there are two elements are there. One is welding and one is processing. So we talked about various variants of friction stir welding technology and mainly the friction stir welding of dissimilar metals and challenges in different variants and its application. Now, in this particular module, we would be talking about more on friction stir welding technology on a processing aspect. And friction stir processing aspects also has many variants. They have a different applications. There are many applications which are written here. I mean, for surface composites, for superplasticity, friction surfacing, friction stir additive manufacturing, friction stir forming, and at the end, some challenges in FSW, FSP, followed by some learning and future direction and about IWPDU MRIP. So kindly pay your attention to the next few minutes on this particular talk. So this is what is I mean, you can say the broad classification of friction stir welding technology. Many new things have also come up in this particular domain. And so we tried to cover the welding element in the first module. And now we will be talking about the processing module in the second phase, which is now. So you can see here that friction stir processing has multiple applications. So first is friction stir processing. Then you can have friction stir channeling, friction surfacing, friction stir surface cladding, friction stir additive, friction stir forming, friction stir extrusion. So I think many modules are written here. So we'll try to cover as much as we can in the remaining time. And we already covered the welding module, and with a little bit of some more informations are also covered in the welding module. So moving further with the friction stir processing. So if you look at the friction stir welding and friction stir processing, the fundamental difference, it is not a joining process. It is mainly for modifying the microstructure of the material, or you can say the modification or modification of the material, especially in case of metallic material. So you will try to improve the property with the help of friction stir processing technique. Now, instead of joining two plates with the friction stir welding tool, this time you would be using only single plate and then run through the FSW tool. So that is nothing but the friction stir processing. So here you are not joining the two metals or two dissimilar metals or similar metals. You are simply taking a one single plate of the material and then you run the FSW tool and you try to refine the microstructure, modify the microstructure and improve for improvement in the mechanical, metallurgical or tribological properties. So here friction stir processing has multiple applications. We would be touching upon some of the application. You can see the applications which are written here for friction stir processing is for superplasticity. It is also used for room temperature formability, in the casting modification or improvement in the casted product properties, the surface composite, the powder processing and channeling. So there are many applications. So what I wanted to tell you with the friction stir processing, there are many new areas which has been worked out with the same FSW tool, with the same vertical milling machine or automatic vertical milling machine with the same fixture, with little bit of modification here and there. You can work out many applications with the help of FSP technique. So FSP is not a joining technique. It is for a modification or modification in the existing microstructure of the material. So, I mean, say, for example, if you see here, superplasticity, you see, if you look at the arrow of superplasticity, it is going with the fine grain. It is going room temperature formability. It is also going with the fine grain. So to achieve superplasticity, the primary requirement is the fine grain structure. In order to get room temperature, good room temperature formability, the fine grain is the requirement. Similarly, if you look at the surface composite, say for example, if you look at the arrow, one of the arrow is going for homogenization. And if you look at the another arrow, which is going for mechanical mixing. So you are trying to add some reinforcement in the matrix, and that's how you can make metal matrix composite here. So similarly, if you look at the casting modification, there are three different arrow, the mechanical mixing, then you have homogenization, and then you have a primary breakdown of the reinforcement particles. So these are, we will understand all of them one by one, and mainly the superplasticity and the surface composite. So to start with, so there is one particular application of friction stir processing is for manufacturing the surface composites. So surface composites, and that too through the solid state route. We do manufacture, I mean, metal matrix composites through the liquid route also. But liquid route has certain challenges and it has its own disadvantages. So with the help of friction stir processing, researchers have developed many metal matrix composite wherein they are tried a lot of reinforcement particles, either with the boron carbide, either with the silicon carbide or Al2O3, TIC. So different ceramic reinforcements which has been mixed in the aluminum metal matrix, I mean in the matrix of aluminum, and then you will get the metal matrix composite with the help of friction stir process.